I will inform you after 9 minutes. So you need to wrap up your remaining slides within a minute so that we can have plenty of time for the question and answer. So this is for all speakers. So I request to please stick with your time so we can have enough time for the discussion as well. And second thing is like I request all the speakers to be present during the whole session. So because at the end we have 15 minutes, which is dedicated for in-depth question and answer and discussion. So it will be fruitful for everyone to have in-depth discussion what people are doing in their area and open questions like what can be done. So with this, I think we can start. Ketki?
Okay, yeah, we
Good.
can start the session.
Yeah.
First, I would like to introduce our chair, maybe.
Mhm.
So today's our chair is Dr. Zubair Sheikh, and he's working currently as a research associate in University of Texas at Dallas. And if you want to state his research interest, then it is solar wind, solar transients, and space weather. Broadly, I would say. And I would give the charge to Zubair now. You can start the session.
Thank you, Ketki, for the nice introduction. Hello, everyone. Good morning, good afternoon, and good evening to everyone. Uh, Welcome to the next session of the day three. So, space weather forecasting and operation. Today we have five talk in this session, and this talk is going to give us a channel to understand solar wind driver to their impact on the Earth magnetosphere and what are the different possibility to understand the modeling approach, especially using machine learning and other technique to incorporate in one chain. So I will invite our first speaker is like Apurva Bhagat. Um, she is going to talk about the turbulence uh, in the CME using wavelet analysis technique. Apurva, the dash is yours. So 9 minutes, I will give the reminder. Uh, Okay, Apurva, can you hear us?
Yes, sir.
Great. So you can start sharing your screen and dash is yours.
Okay. So, hello everyone. Myself Apurva Bhagat. I'm a master's student at ISHA Pune, and I'll be presenting my work on turbulent fluctuations in ICME regions using wavelet analysis. So, the objective of our study is to investigate localized high intensity fluctuations, which we also called as turbulent spots, as signatures of intermittency in plasma turbulence. We tried to quantify these turbulent spots based on the intensity and the occurrence rate to examine their role as indicators of CME or sheath onset, and also if we could suggest that the sites of turbulent spots are also the sites of enhanced proton heating. So this to begin with, this slide explains how geomagnetic storm is a potential threat and how solar storms driven by ICMEs pose real technological risk, and the need to understand the structure that govern the turbulence and how it is important from the point of view of space weather forecasting. So this diagram explains that how solar eruptions propagating towards Earth can lead to geomagnetic storms. So the primary determinants of geomagnetic storm intensity are the southward magnetic field, the solar wind speed, the prolonged southward magnetic field, and the coupling efficiency. But the primary determinants are governed majorly by the structure of a CME and how it influences the storm response. So for that, we need to understand the CME structure. So the background, the shock front, the sheath region, and the magnetic cloud can be understood as the different regions. So this diagram explains how like an overall view of a flux rope CME that is expanding towards Earth. And as you can see, like there are different regions. That is the, if we take the sheath and MC are the major regions that govern like that that lead to the intensity of the storm. So the sheath region is like compressed compressed magnetic field that drives the geomagnetic activity, and the magnetic cloud is a smooth organized field that sustains southward BZ, which leads to intense storms. But all these regions, like the spacecraft records a continuous stream of measurements, but CME substructures are identified only after detailed analysis and model fitting. So in this study, we tried to address the question that can any concrete observables that can identify these regions in real time without model fitting. So this diagram here is like one of my plots where you can understand how the diagram of a CME is related to the time series of different parameters and how the fluctuations evolve during time. For example, the temperature, magnetic field, velocity, and proton density. So the turbulent power to intermittent fluctuations. Earlier, people like tried to understand or drew the difference between the different regions of a CME using the turbulent power. So the in situ CME measurements analyzed suggest that sheets typically exhibit higher turbulent power than background solar wind or magnetic clouds. But this provides a broad averaged picture of energy distribution across CME regions, but uh, it does not tell how turbulence varies in time or space. Also, like energy in turbulent flows is often localized and bursty rather than uniform. Therefore, there is a need to study the turbulence, like energy is dissipated through short-lived localized fluctuations, and this intermittent turbulent spots are similar to turbulent spots in wall-bounded boundary flows in fluid dynamics too. So studying them provides insights into localized energy transfer and cascade mechanisms. So we used wavelets. Why the need of wavelet is that it provides time frequency localization and identification of transient intermittent features. We use Morlet wavelet, which is a complex sinusoid modulated by a Gaussian, which is ideal for localized turbulent fluctuations. We use the continuous wavelet transform. These are the equations. Like if you take S as the signal, then the C gives you like gives you the measure of how much signal is similar, or how much the is convolution is done similar to the signal. We tried to calculate the wavelet power spectral density, that is the PSD, that measures the energy of fluctuations at each timescale point, and high PSD regions indicate turbulent spots. Uh, the integrated power spectral density, as shown, quantifies the total turbulent power for that selected CME event. So, the limit of frequency, that is from COI to F max. The COI here refers to the cone of influence. It's like it identifies the region of the wavelet spectrum affected by edges of the time series. Only frequencies above FCOI are considered reliable for turbulence analysis. So, turbulent spot in CMEs. So uh, this plot refers. Okay, the first panel explains the wavelet power per unit interval in log f space, as in the case with the top panel. Such frequency pre-multiplied spectra are commonly used in fluid dynamics too to identify the turbulent spots. And the second panel is the integrated power spectral density. And here we can associate the turbulent spot in both the panels, and the significance of like the significance of these turbulent spots is that identifying where and how these spots occur can help us understand the turbulent structure within CMEs. This provide insights into energy dissipation, heating, and localized dynamics. It also forms a statistical basis for connecting turbulent fluctuations to space weather effects. So in this figure, I have just plotted using magnetic field. If we plot it for the other parameters too, then this is how the like for different parameters, this is the integrated power spectral density time series, and the colored peaks are the turbulent spots that we are identifying for each parameter. So using this, uh, first thing that we did was we identified the strongest turbulent spots for each parameter, that is for magnetic field, velocity, and proton density, uh, and temperature. So to build a contrast, we took the peak ratios, that is, we identified the largest peaks in different regions and took a ratio. So the mean ratios for, let's say, for sheath, if we take the ratio for sheath region, therefore it would be the largest peak in sheath for magnetic field upon largest peak in background for magnetic field. So these are the ratios for different parameters. And the key observation is that strongest turbulent spots clearly distinguish, like act as a distinguisher between different regions. So specifically for magnetic field, we see like the ratio is very high. And similarly, the other thing is the similarity between the ratio of magnetic field and temperature suggests turbulent spots likely as sites of proton heating. Uh, like based on this, we also tried to see like if we could get some temporal relationship between the
Last one
turbulent spot
minute.
between temperature and magnetic field. So this table explains like the highest turbulent spot in temperature versus the turbulent spot in other parameters, and when they occurred with respect to the temperature turbulent spot. So for magnetic field, for sheath region, we see that the time range is very less. That implies that turbulent spot currents correspond to enhanced energy dissipation, producing localized proton heating, and delay between the peaks with respect to temperature reflects conduction or dissipation or time scales. And also, it requires further study to explicitly state that how these things how these sites can also act as sites of proton heating. This all four histograms uh, like are the representation of the ratios for all the 125 events that we have used.
Apurva, can you wrap up in 1 minute?
Okay, sir. So so the other main thing is the occurrence rate of the turbulent spots. So the occurrence rate is, if we define, it will be the peak density of turbulent spot for a given physical quantity, that is pdx, and nx is the number of IPSD peaks in the considered region, upon, normalized by the duration of the region. So we tried to use this for different number of turbulent spot, let's say for 5, 10, or 15 for each region. And we see that for sheath region, the frequency is that 20 turbulent spots per day, as compared to background or MC, which is very high. And similarly, we have done this for all the other parameters also for different regions individually.
Please wrap up. Your time is about to end.
Okay. So summary is that look, concentrated regions of intense broadband fluctuations, like these are the turbulent spots, and peaks. The other thing is that peaks in all these parameters do not always coincide. Uh, like the turbulent spot in magnetic field will not be in V or N, and the strongest spots in the sheath region are like uh, are occur in sheath as compared to MC or background, and magnetic field shows largest contrast for sheath region. The sheath has more turbulent spots than background or CME. Okay. Uh,
Yeah. Thank you, Apurva. Thank you for
yes.
the nice talk. Uh, we don't have any time to ask the question, like 12 minutes over. but we can have one quick question if someone want to ask, like one quick question. Yes, so okay, I have one question. Like you
Yes.
are using wavelet analysis. So can
Mhm.
you use the wavelet analysis to distinguish between the turbulence and coherent structure within the given region, for example, current sheets in the CM?
So we can, but we have to have some kind of parameter to do that. So this turbulent spots, like many people have also defined this turbulent spots based regions of say high current sheets or higher eddies. So maybe if we have some kind of parameter to quantify them, then maybe yes.
Okay, thank you so much. So let's move to the second speaker. Uh, so our second speaker is Ayushi Nema. She's from Sardar Vallabhbhai National Institute of Technology, Surat. Today she is going to discuss with us the HILCAS event, which is like high amplitude, long duration auroral activity, their effect on this relativistic electron in the radiation belt. So Apurva, the dash is yours. Please share your screen. So I will give warning at 9 minutes. So please wrap up after a minute. Ready? Can you hear us?
Hello.
Yeah.
Yeah.
Please.
Can you confirm that my slide is visible?
Yeah, we can see your slide.
Okay. So thank you for the introduction. I am Ayushi Nema from NIT Surat. I have done PhD there. Today I will be delivering my talk on the study of impact of Hilka events on the relativistic electrons in the Earth's outer radiation belt studied during the Van Allen probe era. So the objective of my study was to identify their impacts and understand how the energy and L shell of these relativistic electrons vary during these events and understand the underlying physical process that lead to the particle energization, and thereafter to identify if there is any wave particle interaction during these events which are causing the flux variation and the energy enhancement. So for this study I took 13 Hilka events from the year 2014 to 2019, which is the Van Allen probe duration. Van Allen probe launched in, I think, 2013 or 2014. And these events were recorded here. On the left side, you can see the list of these events recorded. For this study, I did a superposed epoch analysis and performed an performed an estimation of the interplanetary parameters to see their variation. On the right hand side, you can see a plot showing the average variations of these interplanetary and geomagnetic parameters for these 13 events. The black line, the black solid line, represents the 1 hour resolution of these IP parameters, and the blue line represents the 1 minute resolution, where the red dashed line represents the onset of all these 13 events. The epoch analysis was done on the basis that their onset time were overlapped, and the superposed study was done. After that, I studied the flux variation for various range of particles ranging from mega electron volts to kilo electron volts. For mega electron volts, I used the wrapped instrument of Van Allen probe. For the entire study, I used probe A. There are two probes, probe A and probe B. So for this study, I used probe A. On the left hand side, you can see a flux variation analysis using wrapped instrument, which is generally used for mega electron volts relativistic electrons. The top panel represents the energy variation with respect to epoch, and the bottom 5 panels represents their pitch angle variation with respect to epoch. So it is clearly visible that after onset there is an enhancement in the energy after all these 13 Hilka events. Also, one can notice that there is a delay of 1 to 2 days for the energy enhancement, whereas if we look at the pitch angle distribution of these particle, we can see that for low energy electrons there is a sudden enhancement, whereas as the energy increases this enhancement get delayed by few days. Sorry. After that, for low energy electrons we used MAGIs, same from the Van Allen probe. Here also we observed the energy enhancement after the onset. The same pattern we observed from the RAP, that for lower energy particles the energy enhancement was sudden, and as the energy increases this enhancement get delayed by days. Also, one thing to notice here in these two plots is that the pitch angles around from 60 to 120 are more enhanced. Particles with these pitch angles are most enhanced as compared to the field aligned, that is 0 degree to 180 degree particles, which can further be estimated why this is happening by using wave particle interaction study, which I will show in the later slides. For both the instrument, we can see that the perpendicular particles are showing more enhancement than the field aligned particles. So in this slide, I have shown a superposed epoch analysis again, but in the leftmost plot, you can see that the average was done on all the pitch angle particles, and the enhancement was here also visible after few days. In the middle plot, you can see the enhancement for field aligned particles, and on the rightmost plot, the enhancement for perpendicular aligned particles. So from this figure, it is clear that the enhancement for perpendicular aligned particles are more for higher energies as compared to field aligned particles, and the delay is here is for 1 to 2 days here also. After that, we identify the cause of this enhancement and the delay. For that, we used ground-based and space-based magnetometers. On the left-hand side, we have shown the ULF wave presence. The top two panels, A and B, shows the presence of ULF waves using the space-based magnetometers, and the bottom two panels, C and D, shows the ground-based magnetometers, which are the cause of radial diffusion of the particles, the major cause of acceleration of these particles. So it is clearly visible that for the higher L shell above 4, the enhancement is clear after the onset with respect to time. And on the right hand side also, the power is enhanced for higher L shells only above 4 in the ground based and the space based. After that, we identified that if there is any VLF wave present for the secondary acceleration of these particles, and we encountered that after the onset, VLF waves was also present. The VLF waves were mostly present during the dusk side and the night side of the environment, and they are mostly present at the higher L shell range. So one can confirm that the ULF waves are the major drivers of the enhancement of these particles, and the VLF waves observed using emphasis are the secondary accelerators, and they are generally accelerating the lower energy particles, whereas the ULF waves are responsible for the higher energy particles of MeV range. So, summarizing this work, I have found that the relativistic electron enhancement are observed during Van Allen probe era for Hilka events with the delay of 2 days approximately after the onset, and the energies are extending up to 4 MeV. Beyond that, there was no considerable enhancement, and the perpendicular aligned pitch angle particles are showing significantly stronger flux enhancements as compared to the field aligned, indicating that the preferential energization of the perpendicular aligned particles during the Hilke intervals. Also, the pitch angle dependent response and the delayed flux enhancement response suggests that the strong dependence on the ULF waves for the ionization of the relativistic electron particles through radial diffusion, drift resonance, and Betatron mechanism, whereas the VLF wave contribute to the acceleration of lower to mid energy seed electrons. So these are the conclusion that I came through with this study. For the detailed study, you can scan this QR code or go through the link. I'm ready to take questions now.
Thank you, Ayushi. It's a very nice talk. So, does anyone have a question? I can see one question from Kalpesh. Kalpesh, you
Yeah.
can ask question directly.
Okay, nice talk.
Nice.
Do these events are isolated Hilka events or they are associated with storms? And if yes, if they are associated with storms, then what kind of storms they are? Weak or moderate?
Okay, so Hilke events are actually identified on the basis that they should occur during the recovery phase or out of the main phase of any geomagnetic storm. So to identify them, you have to first look for any storm and the longer recovery period of that storm. So if there is a longer recovery period, then there are the chances that you can identify these Hilka events. Some researchers have also identified these events, like you said, isolated Hilka without any storm, and some has identified just after the storm and during their longer recovery period. So there are various definitions they have used, and none of them is fixed for the study.
Okay, yeah, thank you.
Great.
There
Yeah,
is
we have one
another
more
question.
question.
Yeah.
Yeah.
How did you identify your Hilka? So Hilkas are identified based on the criteria that is detailed on the paper that I have mentioned in my slide. I will share the link in the chat also. You can read my paper there. There is a detailed explanation of how one can identify the Hilka events.
Yeah. Is there any more questions? If not, then I have one question for you.
Sure.
So, in general, Hilkart's events are associated with something called alphanic fluctuation in the solar wind.
Yeah.
You can read a paper by like Surutani et al. There are a bunch of paper in that direction. Did you
Yes.
find any signature of alphanic fluctuation in the solar wind related to all your 13 number of events
Yes.
like?
Yes, I have done a case study and
Mhm.
each event study also where I studied their IP parameters and identify the galvanic nature of all these events because fluctuations was a necessary requirement for these events.
Okay. Yeah.
As I see, the
So how
most
you?
of the storms were in during HSS, as I recall from her second
Yes,
slide. So
yes,
there might
yes.
be possibility of
Hmm.
alvenicity,
Yes, because
maximum.
Yeah.
delta occurs when high speed and slow speed streams create a CIR, and that CIR interact with the magnetosphere and they cause these events.
Yeah. 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 Thank you. Thank you so much, Ayushi, for the nice talk. So
Thank
now let's move to another talk, the next one. And now we are going to connect ourselves from predictive and modeling approach to understand the space weather point. So our next speaker is Sa- Saket Majumdar. Uh, he is working as a space weather analyst in Digantra Industry Private Limited. So he's going to talk about like neural augmented space weather forecasting for uncertainty propagation in Leo conjugate analysis. So, Saket, you have 9 minutes for the presentation. I will give technically 10-minute presentation, then I will give warning for 1 minute, and then please wrap up within a time. So, no, that is your. Please share your screen and go ahead.
All right. Thank you so much, Dr. Zubair, for the introduction. I'd just like to confirm that the presentation is visible and the slides are changing.
Yeah, you can see your slide perfectly.
All right. All right. So, hello, everyone. I am Saikat Majumdar. I'm working as a space weather analyst at Digantra, Bangalore. And I'm going to be talking about work that we did on neural augmented space weather forecasting for uncertainty propagation in low Earth orbit conjunction analysis. So, yeah, um, essentially, the problem statement that we are dealing with in satellite operations is that uh, the atmospheric density is strongly influenced by solar and geomagnetic activity. And two of the primary drivers of solar and geomagnetic activity are the F10.7 solar radio flux index and the geomagnetic index KP. Now, these two parameters are essentially driving atmospheric drag, which is the dominant source of low Earth orbit uh, prediction errors for satellites. Now, with the rising number of LEO satellites and the fact that we just now are exiting from solar cycle 25 maxima, the prediction challenges are amplified in such circumstances. Now, to address this problem, there are climatology-based forecast models for these solar and geomagnetic parameters, but they often fail to capture nonlinear and dynamic space weather effects and variations. And these models are often seen to degrade beyond 1 to 3 days of lead time. So with these challenges, we should understand now that the accurate orbit prediction, which is like knowing the accurate state of the satellites is very vital for collision risk assessment and space-wise safety. So, how is this problem being solved? Essentially, what are the current approaches? So for F10.7 forecasting, there have been multiple studies on like machine learning models, transformer models, LSTMs, and multivariate approaches, which are seen to outperform the climatology-based persistent models that are out there. Now, these models are often offering better forecasts, but the problem is that they are often challenges of like limited multi-day accuracies, and especially that is pronounced more for KP forecasting, where the KP values are forecasts are unreliable beyond 3 days of time. Now, in this work, we actually have three segments. The first one is we capture dynamic space weather variation using VMD LSTM ML-based forecasting models. We develop these models and then we synergize this model and integrate this into uh, orbit predictions, where we compare the ML predictions, the VMD LSTM model, which will be referred to as VL, the forecast with traditional open source forecast that are used in satellite operations to see how the orbit prediction performance improves or how does it impact the performance. And then using these results as our base, we assess the impact on collision probability between two satellites by taking a by taking a conjunction assessment scenario. So this is the architecture of the ML model framework that we developed. We implemented a hybrid variational mode decomposition LSTM framework, where essentially the raw like the data is fed into a VMD mode where it decomposes the data into multiple submodels, and then within those layers, it essentially does the forecasting, and then it reconstructs the sum of the intrinsic mode function forecast to construct the final variable. Now, for the data sources for F10.7 solar flux, we have used almost like 5+ decades of F10.7 data for training the model. For KP, we have used 20 plus years of KP data for training, as well as we have used Omni solar wind data as an input feature that drives the KP model. And we have evaluated the model performance using RMSE and MAE as metrics. Now, uh, the input feature of F10.7 is just the time series history of the F10.7, and the model functions by taking 27 days of history and outputting 3 days of forecast. For the KP model, it takes 3 days of history of KP plus the solar wind IMF parameters, the velocity and magnetic field cross terms, dynamic pressure, and some d by dt terms of the solar wind variables. Now, here is one plot that shows the VL models F10.7 actual versus predicted results. So this is essentially uh, the training, testing, and validation cases for the F10.7 model. So we achieved pretty good results for the F10.7 model during the validation and testing phase, where the RMC and MAE are 1 to 2 SFUs. Now, we evaluate these models' performances by taking this testing framework, where for the forecast performance accuracy, we compare 3 days of forecast of these models against open source space weather forecast available at Celestrak, which is a repository of space weather data. And these forecasts we generate for two test events. One is a quiet event with KP range ranging from 1 minus to 4 minus, and F10.7 range as follows in the table. And we also check the impact on a geomagnetic storm G4 scale of NOAA event. And we do we quantify the impact of the forecast on this event also. Now, there is another way to test. We have basically created synthetic satellite sets with the following configurations. And we have used an orbit propagator with a density model, which takes in these forecasts and generate simulated orbits for the satellites for a duration of the 3 days. And these orbits are now compared with reference orbits generated using true space weather data to quantify how much difference is our model having versus the true space weather data driven model orbits. Now, here are the results for the VL model performance. So for the quiet case, our results are better than the open source forecasts that are available. We can see in the table and plot for F10.7 as well as KP. So while the public forecast had some deviation from the truth, our model actually gave a sort of a smooth forecast, essentially for the quiet event. Now, for the storm event, what we witnessed is that we took a severe storm case, but then the ML model had an issue where it was not able to fully capture the storm event accuracy. But in this case, we are also seeing the F10.7 forecast being quite similar to the truth. So this will have an impact in the orbit prediction results, which I'm going to show in the next slide. So here are essentially the plots for orbit prediction during the quiet event. So on the left, you see one 6U CubeSat at 450 kilometers of altitude. The red signifies the VL model driven forecast, and blue signifies the open source industry like Celestrak forecast. Now, for all the cases in the table, you can see that the VL model forecasts are seen to outperform the open source Celestrak forecast in orbit prediction of these synthetic LEO satellites. Similarly, in the next case, which is the storm event, here we see also that the VL models are actually offering better accuracy as compared to the open source forecast, although even the margin, the difference from the quiet event is much smaller here, as in the model is performing better, but it is the difference in the quiet case was more pronounced than the difference in the storm case. Now, with these sort of results, we move on to the impact in collision probability estimation. The objective of this is to actually quantify how the ML forecast models influence predicted conjunction risks for two satellites that uh, are coming in close proximity to each other. Now, the conjunction test case we took was actually taken from a historical database of satellite conjunctions. So here we studied one Starlink satellite and one Chinese satellite conjunction event, which happened right on the onset of the May 2024 Gannon storm. So here are the satellite parameters that we used for the study. And
Second,
here is the,
last one
yes,
minute.
yeah, I'll finish. So here's the conjunction data and the input data that are used. Now, here we did not have an open source historical forecast available. Hence, the comparison is done only with against true space weather data. So here, what the result that we obtained was that the collision probability that we estimated as opposed to the time before the closest approach, we saw that while the PC values that we estimated using the true space weather data, the VL model were able to match that PC value up to 15 hours before the time of closest approach. Whereas industry standard essentially tells you that any satellite operator needs to make maneuver decisions 12 to 24 hours from TCA. So this sort of brings us to the conclusion where we developed this VFD LSTM model and we performed orbit prediction on the low Earth orbit satellite. And we witnessed that the models actually led to lower errors as compared to open source forecasts that are out there. And when we applied these models into collision probability estimation, we are able to match truth-based result with having sufficient lead time that is relevant to industry conjunction assessment and collision avoidance decision making. So essentially, the future work in this will involve like benchmarking over an extended period of time, testing on more cases, assessing over more other cases, and comparison against other forecasted data, exploring other ML architectures that can offer faster and better accuracy and results. So this work was published in AMOS conference last year, and the paper link is here. So yeah, and here are the references. So thank you, everyone. This concludes my talk.
Yeah, thank you, Sekar, for the nice talk. It's a very interesting one. So, do we have any question to ask? Okay, so I have a question to ask you.
Yes,
So
please.
you have used F10.7 and KP index in your model. Why
Yes,
have you tried like there are KPs like geometric storm indices, kind of one indices.
yes.
So have you tried with other indices, for example, DST
Mhm.
index or CMH index or AU/AL index?
So I haven't tried with those index, and the reason for it is because like all the models that drive satellite orbit prediction currently, the open source models that are used in the industry rely on F10.7 and KP. Now, I'll give you one fact, which is that while there is a model that actually incorporates DST into their prediction of the atmospheric density, which is driven by space weather, that model is not really operationally viable to use. As in, like even if we tried using DST forecast and tried to incorporate that into the model, that model is not very scalable and functional to use in satellite orbit prediction. So that is why the goal here was to actually choose the parameters that can be used to drive forecasts of the satellite orbital parameters as well. Now, while you mentioned, we actually did incorporate DST. I mean, we tried using DST as a function, uh, as an input within the KP forecasting model because KP and DST have some level of correlation, but that did not lead to a significant improvement in the forecasting because in order to forecast KP, we also would need the way DST evolves with time for the forecasted duration. So given that we did not have a history of DST for a storm that we are trying to forecast, so we decided not to use DST as an input parameter while developing the KPML model.
Yeah, thank you. Thank you so much, Sekar, for the nice presentation.
So I'll stop sharing.
You are muted, Zubair.
Yeah, no, yeah, sorry. Yeah, so our next speaker is Sanjeev Agarwal. So she is a PhD student at Indian Institute of Astrophysics, Bangalore. Today she is gonna talk about the development and validation of CAP method using solar orbiter and wind observation. So Anjali, dash is your. uh,
Yeah, sure. Is my screen visible?
Yes.
Hello?
Yes, we can
Thank
see
you.
your screen.
Okay. Thank you for the nice introduction. So I'm Anjali Agarwal working with Vagish Mishra at Indian Institute of Astrophysics, and I want to thank SOC members for giving me an opportunity to present my recent work. So in this work, we have developed a method that is CAP method. So this method can be used or accounts for the expansion dynamics of the CMEs. And we have validated this method by using a unique CME which was observed by or sampled by radially aligned in situ observations of solar orbiter and wind spacecraft. Just for the sake of completeness, I want to give a brief introduction on coronal mass ejections. So CMEs are the expulsions of the magnetized plasma bubbles from the sun into the heliosphere. And when they are ejected out from the sun, they have different angular weights. Their speeds could also be different and they have different masses. And they are propagating in a non-homogeneous ambient medium. This means that their propagation or their evolution will be different as they have different properties itself and they are propagating in a non-homogeneous ambient medium. Also, CMEs are important because of space weather. As we all know that they can produce power, they can lead to power grid failures, electric disruptions, and GPS navigation error. So, historically, CMEs are observed by white light coronagraphic observations. And in these observations, generally or sometimes oftenly, the three substructures of CMEs can be visible, which is shock, sheath, and magnetic cloud. And there is another type of observations which is in situ observations. So these observations are the real plasma parameters of the CME, and in these observations one can also identify the three substructures of the CME as they are different from the ambient medium. So in this work, I am using in situ observations to understand the expansion dynamics of a CME. So, earlier studies have assumed that when a CME passes over an in situ spacecraft, its expansion speed remains constant during its passage. Now, in this animation, we can see when a CME is passing over the in situ spacecraft, it is expanding also. So this expansion speed could be constant or not constant during its passage. But if it is assumed to be constant, then it can lead to certain uncertainties in prediction of the arrival time of other CME substructures like the center and trailing edge of the magnetic cloud, radial size of the magnetic cloud, and its duration as well as its magnetic flux. And these uncertainties will be more in this era when there are many in situ satellites which are approaching near the sun, where the expansion speed of the CME is higher and CME has higher acceleration. So to overcome from this limitation, we have developed a method which is CAP method. And this method can accounts for the instantaneous expansion speed of the CME. And after accounting for instantaneous expansion speed, it can give us the total duration, exact duration of the magnetic cloud, magnetic flux, and radial size and other parameters. So this is the schematic of the method at three different time stamps. At first time stamp, the leading edge of the CME is arrived at 1 AU, and we don't have any in situ measurements of the other substructures like its center and trailing edge. Similarly, when a center is arrived at 1 AU, the cloud is expanding and we don't have any information of the leading edge and the trailing edge. If we assume acceleration of the substructures is constant, then we can find the measurements of all these substructures, leading edge, center, and trailing edge at the same time stamp. Now this is the workflow of our method. So we can estimate this the acceleration of this substructure either by using remote observations or by using multiple in situ measurements which are radially aligned. And if we have acceleration, then we can estimate the propagation speed of each substructure, then instantaneous expansion speed. Now we want to validate this CAP method by use with the in situ observations. Now to validate this method, we need the instantaneous expansion speed from the observations. The instantaneous expansion speed from the observation is only available if the radial separation between the two spacecraft is must be comparable to the magnetic cloud radial size or half of its radial size. And this can be possible in this era because PSP and SOLO are exploring the interplanetary medium beyond 1 AU near to the sun. So we did an extensive data search for those events which are measured by at least more than one spacecraft, and then we have ended up with only one event in which the radial separation of the between the two spacecraft is comparable to its radial size. So the event is of 3 to 5 November 2021 event, and the event is very unique because when the center was sampled by wind, and at the same time solar orbiter was sampling the trailing edge of the magnetic cloud. This means that from the in situ observations we can estimate the uh, instantaneous expansion speed of the magnetic cloud. So these are the in situ observations, and these are the different structures: shock sheath and magnetic cloud. And this is the overplot of the magnetic cloud at solo and wind. From the observations, we have estimated instantaneous expansion speed, and we have used the 2 point radially aligned measurements to find the acceleration of each substructure. Now we have implemented this acceleration in our CAP method to estimate the instantaneous expansion speed from the method, and we find that the CAP method estimates is matches well with the observations. So this was the one aspect of the study. We have validated our CAP method. Now we have opportunity to know the evolution of CME substructures, as we have radially aligned two spacecrafts. So we have data investigate the evolution of the shock first, and we have estimated the shock speed, Mach number, and other shock parameters. And from all of them we have find that the shock parameters are higher at wind. As we can see here, shock speed and Mach number at wind is more than its speed and Mach number at solo. This suggests that shock is strengthens at a larger distance from the sun, which is a very rare case. So now we have thought to understand the evolution of the magnetic cloud, or investigate the evolution of the magnetic cloud from solar to wind. And the evolution of the shock motivates us to investigate its magnetic cloud evolution. We want to know the evolution of the magnetic cloud is normal or unusual, like shock evolutions for this CME. So these are the theta and phi of the magnetic field vector. From this we have noticed that orientation of the flux rope is highly inclined, and the flux rope has E and W type of orientation. And we can also find the orientation of the CME or the magnetic cloud from the minimum variance analysis technique. So we have implemented this technique and identified the orientation of the cloud. But we from this analysis we have noticed that the cloud is low inclined flux rope. This means that widely used technique, which is MVA technique, has some discrepancy with the visually identified flux rope type. Then we further find the poloidal magnetic flux using the force-free flux rope assumption, and we notice that the poloidal magnetic flux at wind increases by 24% of its value than at solo. This further suggests that the magnetic flux of the magnetic cloud is not conserved, and there is some additional flux injection from solo to wind. So our detailed analysis suggests that for this particular event, for its evolution of the shock and magnetic cloud is unusual because of the preconditioned ambient medium. So in this case, there was a high speed stream behind the trailing edge of the magnetic cloud. So it already uh, decides the evolution of the magnetic cloud. So in our study, we have validated our proposed CAP method, which can estimate the instantaneous expansion speed of the magnetic cloud. And we find that the shock associated with the CME may strengthen at larger distances from the sun. And we notice a discrepancy of a widely used MVA model with the in situ observations. And the conservation of magnetic flux in the magnetic cloud is violated. So the unusual behavior of the selected CME is due to a high-speed stream at its rear. Therefore, predicting the physical parameters of a CME is very difficult if the role of the surrounding ambient medium is not quantified accurately. Therefore, we are lacking an understanding of how different physical processes operated within the CME and the surrounding medium. As a result, the accuracy of space weather prediction is still limited. Thank you for your attention.
Thank you so much. You are perfectly on the time. Thank you. Very nice talk. So, any questions from the audience? Yes, I can see one question from Davis. Davis, you can ask directly the question if you want, or shall I read the question?
Yeah. Hi, Angel. It's a nice talk, nice work.
Thank you.
So I was just asking that can there be some local heating if you see the in situ plots of solo and by the wind? So can there be any kind of local heating, like partial localized heating between the front and the rear part of the same event? So it was the question. It stuck.
Okay. Can you repeat, please?
So if you see the plots of the like observed by Solo and Wind, so there can be a possible source of local heating in the like front part or in the rear part. I'm not exactly sure which has the higher value.
Yeah.
So
So higher one
have
has,
you?
sorry, the rear part has the higher value.
So could you please comment on it? Like why it can be so because of the same event we have? Yeah.
Yeah, so we have identified the boundary of high speed stream also in this case. So
Mm.
we are thinking that there could be possible signature of magnetic reconnection at the trailing edge of the magnetic cloud.
Acha. That can be a source of local heating.
Yes.
Okay, we can speak about it later. Yeah, thanks.
Okay. Thank you.
Yeah. Any other questions? If not, then I have one question, quick question. So have you tested your method with other CME as well? Like how robust your method is?
Yeah, we have not tested yet with other CME because we have not find any other cases like this, as this was the only event we have find. So the method robustness still depends on the acceleration estimates. If the estimates of the acceleration are accurate, then it will give us good results or reliable estimates.
Okay, so what is the error bar typically in the estimated parameter in your case?
So in this case, it was nearly matching within a plus minus 5 km per second instantaneous expansion speed. Because acceleration is estimated basically by radially aligned in situ spacecraft.
Right. Thank you so much.
But in future study, we will find some more results to estimate acceleration, like using remote observations.
Thank you, Anjali, for the nice presentation. So
You are again muted, Zubair.
yeah. So let's move to our next speaker, which is last talk of this session. So Abhijit Banerjee from New Alipur College, Kolkata. Abhijit, are you here?
And
I
now
don't
he
think
is
so.
not here.
Okay, so if not, then we can have plenty of time for the discussion, right? So that is for everyone. If someone is interested to ask the question, then they can directly ask the question. There are a few questions in the chat box I can read, but people are free to open the mic and they can ask directly to the speaker. Okay. If not, then let me read the question. There is a question for Apurva. Yes, I think the question is like, does the turbulent directly involve uh, proton heating or any other processes in between?
Uh, Sir, so I don't, I mean, they are not. It doesn't say anything about the mechanism of proton heating or anything. These
Mhm.
turbulent spots are mostly the regions where, like, you can find that the dissipation is strongly enhanced. These are the regions where you could, like, where most of the, energy is dissipated, or like, I mean, they are localized in time. So I don't think so. Like the processes like magnetic reconnection or other processes that could, involve like or have direct influence on proton heating. But turbulent spots might not.
Okay, thank you. So we have another question from Kalpesh. Kalpesh, can you ask directly?
Yeah, means my question was about, is there any frequency threshold to identify these turbulence spots? Because as I recall in her presentation, these typically observed in particularly high frequency region where the power was high. So is there any threshold beyond these frequency these spots are there? So
No, sir. Actually, there was no cutoff for that. The turbulent spots can be observed in a wide range. The only thing is, at high frequencies, those are most prominent structures. Like they are observed very well. So no, we did not take any cutoff or anything.
okay.
Uh, yeah, there is one more question from Saket. You can ask directly to the speaker.
Yeah. So first part of the question was, I think, similar to what Kalpesh was asking, that how do we exactly define the IPSD, like the turbulent spots from like the IPSD data sets? Uh, Now, I think she already answered that. Now, the second question I also had that, Apurva, did you try to correlate the occurrence of these turbulent spots with any like negative DST, or like basically any geomagnetic storms that might have happened with these during that event?
Okay, so actually, this is the next part of my work. I'm trying to see if we could correlate the turbulent spot occurrence rates with the temporal correlation. If you could find any temporal correlation between the indices and the turbulent spots, or like which parameter correlates well with the indices. So right now, like I haven't tried it, but that is the next step that we want to try.
Okay, understood. Yeah, thank you.
Yeah. So in Apurva's presentation, I was wondering, you showed the plot period versus time interval versus power, and you put the some dots on some fluctuation, and you name it as like a turbulent spot. My question is like there are other turbulent power which was much higher in the different interval. Then why you didn't call them as a turbulent spot? What makes you what is the threshold criteria you are using to define intermittency in general? And you mentioned also that there dissipation is happening, dissipation is not happening. So have you estimated the dissipation rate or dissipation quantity quantitatively, or you are just um qualitatively explaining on the basis of some theoretical understanding?
So we did not quantify the dissipation rates or anything in this study explicitly, but we
Mhm.
are just suggesting that like there is no specific cutoff that we are taking. We are just saying that the highest peaks that are occurring in the plots like of the integrated power spectral densities, and we are just trying to see like we are naming the highest peaks as turbulent spots, and based on that we are suggesting that the wherever these turbulent spots are occurring in which regions, and the intensities, the contrast, can be used as like to distinguish between these regions. So this was the main thing that we tried to understand. And the second thing is these regions can also act as uh, like uh, regions where like energy dissipates more or similar things.
Yeah, got it. And I have one more quick question for you. Uh, I understand like you are using this wavelet power to quantify which region is more turbulent and which region is not turbulent in general. So you showed one example of CME kind of thing where you have like quiet time, then disturb time kind of situation, sheet and then cloud. So my question is like, it is very well known fact that if you are talking about the CME, ahead of the CME is a solar wind, behind the CME the solar wind, sheet is highly turbulent, matic cloud is highly ordered structure. So with your analysis, what new input you are giving to the scientific community, which is very useful to dig out a certain aspect of the CME which is not known so far.
Okay, so I mean, structure wise, we well understand like which structure like follows what, but the point of view from space weather forecasting, like we do understand these structures, and it's like like most of the work of understanding these boundaries is done post process work. Like we don't have any observants or determinants that could identify these regions in real time. So what we are trying to suggest is like when we get this continuous data points, information. So is there any way that we could use these observables to come up with some kind of uh, thing that we could identify these regions in real time? So that based on
No,
this, if we could use it as an input for modeling different models or something like that.
no, no. Thank you so much.
Okay.
Do we have any questions? Please raise your hand. You can drop your questions in the chat box. We can ask on your behalf if you are feeling a little bit shy to ask the questions. If not, then yes, uh, I have a question to ask to Anjali, especially. So, uh, I, are you using your CAT method? You developed method to estimate CME dynamics in general. So, are you thinking to integrate your methodology to give kind of operational forecast pipeline in a near future, or you are still developing those methodologies?
Yeah, in future we are aiming to do that, but still we are developing. We want like robust to make this method as robust so that we can
Mm.
achieve as minimum as possible error in the acceleration estimates so that the method will be robust. So
Yeah,
still,
so I remember the acceleration estimation methodology itself depends on bunch of assumptions,
yeah.
right? So I do not remember the exact number, but yes, there are big error bar associated with it. So that means, are you going to develop some kind of new method to improve your acceleration estimation, or like you will just develop this your C CAT method and not willing to improve any new methodology to underestimate this, the acceleration parameter of the CME?
So like we are still finding a good way to estimate the acceleration. Then like method is developed, but the way to estimate the acceleration is still we need to quantify. But now in this era that can be possible because there are multiple remote satellites. So from remote observations also, we can estimate the acceleration of substructures by tracking them from corona to the heliosphere by heliospheric imagers also. So we will first find the acceleration from remote observations, then we first implement our cap method using those accelerations, and then find whatever is the result or not, it is still giving our best estimates or not, or it's in the error range.
Yeah, got it. Any questions from the audience?
Yeah, hi Zubair. So I have a
Yeah, hi.
question to Apurva. It's not a question, it's a kind of a comment actually. Apurva, you can hear me? Hello.
Yeah, hi Devesh.
Yeah. So I have a question. So you can so it is for only isolated ICMEs, right? Isolated ICMEs with association of a sheet, like sheet
Yes.
plus MC, the cloud structures. So you can also try to look for ICME interactions, like for example, where you can find a good interaction region in between the clouds or something, and can try to see if you can find such spots in in that area. Actually, it can I think it can help you to understand the physics of the sports. I think
Okay.
it's just a comment. Yeah. Nice work. Yep.
Yeah. So I have one question to Saket about your model. So
Yes.
your model is totally data driven, right? So
Yes, data driven,
so
but yeah, please go.
yeah. So are you like uh, is there any plan to include something physics based model to improve the more accuracy or reduce the error bar in the current model in spite of
Yeah,
data driven?
yes. So the thing is that if we are talking about F10.7, so solar flux, of course, using a data-driven model it's easier to replicate or forecast this parameter because of the fact that it has a periodicity. So there that is why any model that forecast does long-term solar cycle forecasting or long-term solar flux forecasting performs much better. And so there, even if you use there like there, I think there are many other models also which do solar cycle forecasting, which are backed by physics that model the solar dynamo. And so even if we use that, there would not be a significant improvement in the parameter of F10.7. Okay, that is for only the flux. So that we have seen in some literature. Whereas if you are talking about KP, now geomagnetic index doesn't have any periodicity, inherently nothing, because like it is completely like it. So the time series is treated as a random number distribution with only the fact that the frequency of events increase during solar maxima and the frequency of geomagnetic storms decrease during solar minima. So that is the only periodicity that exists. But if we train using long-term data, there will remain uh, some drawbacks to the model. Now, for KP forecasting, of course, like I was looking for some physics informed modeling. So that is why while using the input like feature engineering, I incorporated the dependent variables such as BZ and the cross terms of the like the velocity, number density. So we tried with almost all of them, all of these parameters. Now, of course, when we are doing the forecasting for the next 3 days of the storm, so unless a storm has happened, uh, we will not notice in the true data the southward like the high negative BZ manifesting in the true data while we are doing the forecasting. It will only manifest when the event actually is ongoing. So that is a drawback for which even having dependent variables may not always lead to good forecasting results. So yeah, I think I am open to I'm try more approaches to circumvent this problem. Maybe For example, I can use any solar wind model that forecasts these parameters and use those forecasts as the input to drive the KP model. That is also something that can be done, as in use like these parameters from the WSA and wind model or
Mhm.
any other solar wind model.
Yeah, because if you are using the data-driven model, as you mentioned, the major limitation is like if you don't have a data, you cannot do anything, right? You cannot
Correct.
predict. But so that means we need to have something which is data-driven as well as physical understanding what is happening. Then
Yes,
only we can fill this gap between, for better space weather forecast. So we need some
absolutely.
kind of synergy between the physics as well as what's going on, and you have a data, you can train your model. But if you have more, if you involve physics-driven, approach as well, then you can literally predict like what could be the possible output
Yes.
in upcoming moment of time. So
Yeah,
I
yeah.
think
So
I think the community need to look into the challenges, like how to connect the physics-based model as well as data-driven model to better forecast the space weather
absolutely. Yeah, that
in
is
future.
interesting. Like that is a important future direction to take
Exactly.
because there is still a bridge that exists, like there is still a gap that needs to be bridged
Mhm.
between, when we do like CME and solar wind forecasting and how that will manifest into magnetosphere, ionosphere, thermosphere system. So that gap,
Right.
if we can fulfill that gap, that will greatly, help in the application side of space weather, wherein we can use these parameters to figure out how, for example, GIC, how
Mhm.
ground-based GIC manifests, how the ionospheric
Yeah.
perturbations happen, how
Exactly.
thermospheric changes drive satellite operations. So yeah,
Right. Right.
it's all connected basically. Yeah, that's an interesting direction to look at.
Right. Yeah. So I think people need to come forward uh, to to talk to each other.
Yeah,
Exchange the idea like how
absolutely.
to approach, how to tackle that problem in the front light in upcoming coming years. Then only it is possible to have full-fledged model which can give a much better prediction in terms of space weather point of view.
Absolutely.
Do we have any questions in a chat box? No. Okay. So I have one question regarding the radius orbital dynamics. Maybe. Uh, um, yeah. So in a talk, it is mentioned that at the zero epoch to the left, there was less flux. At the right, there was a high flux, especially in the low energy channel of the electron. And I can clearly see if you're moving from low energy to high energy channel, there was kind of uh, a shift in the onset time of the flux. Can you please comment on that? What could be the reason for that one? Like why you observe a delay in the onset time of high flux?
Uh, we studied that delay after the epoch of those events as a wave
Right.
particle interaction. So we identified ULF waves as the major driver for the radial diffusions of these particles and drift acceleration that is going on for high energy MEV relativistic electron particles, and for low energy particles of KeV range, we identified that the VLF waves are playing a role in um, causing that delay and
Actually, I can't hear you. I think we lost you.
there
Okay. We can't hear you, Ayushi.
are uh,
So
by
yeah, I think there is some network issue from that
the
side.
drivers.
Hello. Yeah. So is there any questions to ask to any of the speaker? If not, then we can wind up because we are on time. So yes, we understand several things from this session. Like session starts with the drivers like CME to understand the turbulence and understand the kite condition, kite period, and turbulent region in the CME. Then the session went to the if impact of the CME on the Earth space environment, especially the radiation belt dynamics. Then we moved to, okay, let us try to understand from the model perspective to understand the forecasting of certain space weather phenomena, for example, satellite drag and LEO orbit phenomena. Then we again jump back to the kind of model-driven understanding of the CME uh, uh, to understand the large-scale structure evolution and derive certain parameter, which is critical to understand the driver as well as their effect on the near Earth space environment. So I think this is like very wonderful session. Thank you so much for all the presenters and all the participants to attend the session. Thank you so much. Pratik, any announcement?
Thank you, Zubair. So we have almost 10 minutes break, 8 minutes now.
Mhm.
Ankush is also here. Uh, I see Judith is also here. Uh,
Yeah.
Yes, guys. So
Hello.
nice session, nice discussions. I'm just listening. Same way.
Now I see actually in India, there are several people who start doing this turbulence in this CME and all the stuff. This is nice.
Yeah.
Yeah. Nice thing in a case like we need to understand kinetic scale thing which is happening in the CME. Like,
Yeah. You also have worked on some this stuff part earlier, right? Small scale
yeah,
flux ropes, turbulence, and
yeah, I'm still working on this turbulence, but a little bit different approach to understand this kinetic scale current shifts in the CME. And the thing is like CME look like they doesn't have a current shifts, but it is like a full of current shifts, like
yeah,
more than 200, 300 current shifts in the CME, even in the flux row boundaries. And they play a very important role in the turbulent dissipation, especially to understand this spectral break and dissipation part of the turbulence.
yeah, yeah. More you understand turbulence, you'll feel you don't understand.
Yeah,
A lot of things happen.
it's a very vast topic. Theoretically, from model perspective, simulation perspective, from observation, of course.
Riturdeep, Can yeah, yeah. Yeah, Joe is here. Hi, Joe.
Hi, good afternoon.
Hello.
So I'm at the right meeting, right?
Yes.
Yes.
Very good.
Congratulations on Proba 3.
Thank you. Yeah. Yeah, we are not yet fully there, right? We will start the nominal operations in May, so everything has to go fine. But up to now, all the messages, everything is positive.
Okay, that's great. We are waiting for others. We will start in like 5 minutes or something.
Okay, Devendu is also here. Yeah, great.
Pratik, I'm around. Just give me a moment setting up.
Yeah, sure.
I see that you guys have been pretty fast with the poster. Thank you very much. This was a last minute change. Shankar had apparently some travel which he had to do at the last minute. So you can hear me loud and clear, right?
Yes.
Yes.
All right. And the video is on? I just put on the
Yep.
video. All right, perfect. Very good.
Hi,
So I hope that
Devendu.
Karthik will join us soon. Hey, how are you?
I'm fine, thanks.
Good to see you.
Yeah, long time.
Yeah, not very long time actually. That was when in January we met in Tiruvananthapuram.
Yeah, but we lost the spacecraft in between and found it back again.
You found it back again. It was so good. I was feeling so bad for Andre, but it's so happy that you found it back again. So is it back to operations and you have observations coming in again?
No, I just mentioned a minute before that beginning of May we might start the coronagraphy flying again.
All right, great. This is good news because actually I was planning to make some predictions for the corona, which Andre was supposed to validate with the Proba 3 observations. So
Yeah,
now
go
we are
ahead.
back in business again. So
Yeah.
So we are expecting Judith.
She is
And
here.
Amal Chandra. Judith is here already? Okay, great.
Judith
Hi,
is
Judith.
here, yes.
And so Shankar is not joining us. He called in like a couple of hours back saying he had an unanticipated travel to Chennai. So he had to drop out. We have found a replacement for him. It's Karthik Kumar. He is the co-founder and CEO of Sat Search, which is right now a European-based company, but they work out of India, Europe, and various other places, and is doing his PhD in Delft University. So I thought it'd be pretty good because he's like, he has one fit in academia and the other fit in industry. So it'd be good to have him over. And then Amal joined already?
Don't
No,
see
I
him.
guess not.
Okay.
yet. Yeah.
Let me actually give a call to both Karthik and Amal and make sure that they remember. Judith was a bit confused about the time, but I guess she should be fine now. I clarified it. All right. Timing, of course, is a bit bad, given that it's Friday late evening in India.
I think Karthik has joined now.
Karthik has joined. All right.
Yeah, I'm here.
Hey, Karthik. Great to see you, and thank you again for signing up
Yeah, no
on a
problem. Happy to
very,
chip in.
very late notice.
No problem.
Amal is also here now. Great.
Amal is here?
Yeah.
All right, great.
Perfect then. We can start with the session now, I guess. So welcome all to the last day's panel discussion. And today we have a very interesting topic. As a solar physics researcher or heliophysics researcher, we all want to know how our research is translated into operational and industrial application. And also we want to know how agency's perspective is in all this situation. So our today's panel discussion is exactly about that. So I first like to welcome today's panel's moderator, that is Professor Dibedu Nandi. He is an astrophysicist with a very, very wide range of interest, spanning across solar and stellar physics, exoplanetary sciences, and our ISHA's this year's theme, space weather. He established CESI, which stands for the Center of Excellence in Space Sciences India at ISHA Kolkata, which has been at the forefront of developing space weather forecasting models. He has previously held two successive terms as Vice Chair of COSPAR's Space Weather Panel and is currently the President of Commission E4 of the International Astronomical Union. He has been actively encouraging industry, academia across the Indian space sector. So now I want to give the charge to Dibendu and we can start the session. Thank you so much.
Thank you, Ketaki. So it's a pleasure to welcome you all to today's panel. So one of the unique aspects of this particular oral symposium is this ideas of hosting different panels on different days of the symposium. And when I was being consulted as an advisory committee member for the symposium, this is one of the panels that I suggested. In fact, a panel I wish to convene as well, because this is something that I am also personally deeply interested in, which is to see the technologies and the expertise that we are developing in academia transition into industry. Because one of the both opportunity as well as a challenge that we face as academicians is that we produce a lot of students, but not everybody is going to find jobs in academia. This is certainly a problem in India, and I'm sure this is a problem also in Europe and in the US. The problem also is an opportunity in the sense that people who are well trained and have specialist expertise which can be utilized for industries can make a transition to the industrial sector and thereby provide a bridge between the academia and the industry. So it's a pleasure to welcome today's panelists. Let me start by introducing them with Dr. Judith Di Patol, who is the head of the Space Weather Operations Group at the Royal Observatory of Belgium, ROB SIDC. Amongst her key roles are managing the 24/7 operations of the space weather forecasting team within SIDC and overseeing the research to operational translation of models for ISHA's international stakeholders, focusing on space weather services. We have also with us Dr. Joe Gender from the European Space Agency, who is a senior scientist there. Amongst his key roles, he is the project scientist of the Proba 3 mission. And in India, we know Joe very well because we welcomed him here for the launch of the Proba 3 mission from Sriharikota, and he was also part of the ISHA ISRO Space Science Cooperation meeting with the themes around Proba 3 and Aditya L1 that happened recently at Thiruvananthapuram. So great to have you again, Joe, amongst us. We also have Amal Chandran. Dr. Amal Chandran is co-founder and CEO of Hex20, which is a small satellite development company. He is also the small sat group lead at LASP, University of Colorado Boulder. So amongst his key roles and past activities, he has been an architect and leader for the Inspire Student Satellite Program, through which he has worked with students at, I believe, Institute of Space Science and Technology and elsewhere in Indian university systems to develop small sats involving students and actually flying them and operationalizing them, collecting data, and doing research with that. He's been also the vice chair of the COSPER task group on small satellite constellation and program manager for NASA's missions such as APEX, Sunset, Dialogio, and Mantis. So welcome, Amal. Shankar was supposed to be part of our panel, but he had to unfortunately step out because he had a sudden travel engagement. And under very short notice, I could pull in Karthik to this panel. I know Karthik for a very long time from my early days as part of this maverick group of space science and startup enthusiasts in space sciences known as New Space India. So Karthik is a CEO of a company called SatSearch, and I'll let him speak about it when he gets a chance to speak. He's also a co-founder of the same company. More importantly, Karthik is also a PhD student in planetary sciences, just completing his PhD at Delft University. And so therefore, he brings in expertise, not just from having founded a startup company, which is doing very well as a student, but also the academic perspective. And I thought he would be a very good fit into this panel. So what I would like to do is, before we get into the discussions and the question and answer sessions, is to give each of you about 3 minutes to speak about your own perspectives in general about industry academia relations and the prospects that students and scientists in our domain working in space science, space weather, and solar physics may have in terms of making inroads into the industry. So let me start with perhaps Judith. Do you have a presentation to make? In which case you can just share your screen. I request the organizers to give everybody in the panel co-host opportunity so that they can share the slides if they have it. All right, go ahead, Judith.
Hi, I hope you hear me well.
Yes, I do, Judith.
Yes, excellent. I don't have a presentation. I will quickly explain somehow with words our perspective, and also our experience. So indeed, I'm working here at the Royal Observatory. It's a federal institution, so we are not academic. But we work with universities within Belgium, which are fully academic. We have PhD students that work partially at the Right Observatory or institution and partially at the university, because at the end, the university is providing the diploma of PhD, of a PhD, not this federal institution. We are also working with the industry, and there is some different relation. So with the industry, either it's a specific contract and they provide us a specific service, IT service general, or specific development, and that costs a lot. So usually we prefer to work in-house. And then the industry is also our stakeholders. So stakeholders means, like, for example, the power grid institution or power grid entity, which is also in the industry. We contact them and we have a close relationship, but it can be also many other industries such as aviation community, etc. So that's another channel, an exchange that we have with the industry. Yeah, and then to kind of give you the global picture. So we are a forecast center, and then the forecast center, it's somehow the in the middle between the academic that does work which is more fundamental research, research and development, that we try to translate it into some operation, so that the forecaster on duty 24/7 can assess, study on a real-time basis, and then provide some important information, interesting or selected information into the industry sector. So based on this and based on this perspective, etc., that we have with the industry, and also related to your question, yes, not everyone can get a job in academic. It's true that coming back to this, within the industry, we have a huge difficulty to talk to each other. The industry have not the knowledge of space weather. And therefore, there is a lot of work that has to be done in its public awareness. But even public awareness is not sufficient. And we really like when a PhD student or someone that comes doing some master training, etc., at the observatory, and then go to the industry, because they go to the industry with a specific knowledge. And with their knowledge, they somehow teach the industry. And then we can discuss later, and we meet them later again, and we develop space weather work, space weather information for them who have already some knowledge and some experience in the domain. And that's much easier. If I can do a parallelism, is with the weather. The weather is something that we study a lot in the academic sector. A lot of students get weather, terrestrial weather training, and then they go to the industry and have this background. And then it's much easier to give them a service and good information when they actually know about what we are talking about. Here, this bridge in space weather is remained very hard. The industry are not yet fully aware of what's going on, what is space weather, how they need it. Now, since we're in the middle, what are the contacts with the exchange with the academic? As you know, space weather and forecasting space weather is still very, our capacity is very limited. We are not good enough. The stakeholders expected much more for us. And therefore, we are lacking massively of more knowledge, more fundamental study. And this must come from the academic, from PhD students, of the work of scientific development. This is a must that needs to grow massively, because yes, our forecasting skills are still very limited. So I think I've done some picture. I don't know if you have a question or comment.
Yeah, no, thank you, Judith. So I think what I would prefer is to go through everybody. I have
Yep.
noted some points in my mind that we talked about, and I think I'll come back to you after we go through everybody. Let me now get in Joe into the middle. And Joe, if you would like to say a few words to begin your engagement in this panel, and I understand you have a few slides, and we'd be happy to post them. Maybe you can just share your screen, Joe.
Yeah, I'm trying. Just give me a second.
Sure.
It asks me that I have to give permission to the tool. Let me see.
Oh, okay. Can the organizers please give Joe permission as co-host?
Yeah, but I think it's a security issue here. Wait, let me see.
Joe is already a co-host.
Oh, you are already a co-host.
Actually, can somebody share my slides? Because I think
Yeah,
I
you have his slides. So can we just share it? He had emailed the slides.
Yeah, because I would have to quit Zoom and dial in again. This might take too long time.
Amal or Karthik, do you have slides, or would you like to just speak?
I have slides.
You have slides. So while we are waiting for Joe's slides, maybe if you can just also try if you can share your slides, then that'd be great. Amal, go ahead.
You can see my slide though, right?
Okay, we can see your slides. Yes, perfect.
Okay. Do you want me to speak?
Yeah, please go ahead, Amal. Yep.
Right. Yeah. So my name is Amal, and I think I'm probably going to be wearing my academic hat today. I'm just going to speak about the work that we do at the University of Colorado. So this is a very interesting topic. Thank you for inviting me, Divyendo. And Judith, it was nice to hear your perspective on from the the space where the operational and forecasting part. I do a lot on the research side of things. So I do a lot on the instrumentation side. And at LASP, we are actually NASA's largest CubeSat center that supports space weather. And NASA is a research organization. So a lot of the NASA heliophysics as well as space weather research is not meant to be operational. So there is a significant difference in the research to operational in terms of the data latency or the quality of the data or the continuous stream of data that you need to make operational and forecast models. So we have done quite a number of heliophysics missions that have that have completed their life, and some of which are in development for for future missions. A few that I would like to especially highlight here. One is called CERBI, which was a radiation belt experiment that looked at transitionary radiation belt characteristics during solar storms during the current solar maximum. We have another one called Sunset, which is solar coronal emission tracker, which is expected to be a mission that can actually replace SUVI, the UV instrument that's on the GO set of satellites, and it's from a CubeSat. And then we have some thermospheric drag and density measurements as well that we are doing. So CERBI actually flew. It completed its mission last year, but it was looking at radiation belt. So it was flying it was flying LEO. So it was transitioning all of the radiation belts, and we were getting a range of particles, in different energy ranges. So high energetic electrons as well as energetic protons in the radiation belts while we were making these measurements. And some of the results are highlighted here. So as it transitions from the in LEO, you get the inner belt, you get a slot region between the inner belt and the outer belt. And when we had some solar flares, we could also see some temporary belt-like characteristics of particles that actually formed. So a lot of these publications have come out. Shinlin Lee was the PI. Again, you get really nice measurements, you make good papers, but how does it transition into an operational model is quite a challenge. And we actually depend on agencies like NOAA to tell us, what kind of measurements and what latency these measurements are needed for us to be able to have maybe a multiple measurements of these to be able to have useful insights for the forecast agencies. By itself, it has really good research potential, but not necessarily the operational characteristics that people like Judith are looking for. Sunset, again, it's going to be on a dawn dusk mission, so it's going to kind of see the sun all the time. But what's really interesting about Sunset is that it's a UV telescope in the CubeSat, and instead of a coronagraph coronagraph, you see the full disk of the sun. Sunset's supposed to fly next year, but basically the slot region that gets blocked is actually covered completely by sunset. You get the full disk view, and you can see the acceleration of the CME as it comes from the sun. So traditionally, this region gets blocked by a coronagraph, and you don't see the acceleration of the CME till it leaves it. But in this mission, because you are doing the full disk imaging, you get the acceleration of the CME all the way. So it can lead to better forecast in terms of how fast is the CME going to reach Earth, and affect, and what's the particle density going to look like, as it reaches it. So NASA's really keen on this instrument. We are too. The spacecraft is ready. We are now awaiting a suitable launch. We did not get a dawn dusk, which is really the vantage point that you want to be in to make these measurements. But hopefully it'll fly by the end of the year. Another measurement that we are making is the DynaGlow mission. So DynaGlow is a 2-satellite constellation, and we are looking at, again, it's a UV imager, but it images the thermosphere in 3 bands, and it's a string of pearl configuration, so we can see propagating gravity waves in the two subsequent measurements. And we look at thermospheric density in this. It's a string of pearl configuration looking at 135 nanometers for the thermosphere. It can be used as an auroral imager as well. So that's another, really keen measurement that the community needs. Again, these are very one-off research-oriented missions, and translating these to research, to operational, having operational value is something that we really look at the agencies to let us know what we can do to do that. I think I'll stop presenting now, and then later during the discussions we can take questions on these. Thank you.
Thank you, Amal. Do you have Joe's slides ready? Pratik, can you confirm?
Yes, we have it.
All right. Great, perfect. So Joe, you can take
Yes,
over.
wonderful. So good evening, everybody. My name is Joe Zender. I'm the project scientist of Proba 3 at ISHA, located in the Netherlands. Can you go to the first slide, please? The one before. Yeah. Quickly, the pillars of ISHA, which is science, space transportation, Earth observation, navigation, commercialization, industry and competitiveness, space safety, connectivity, secure communication, technology, operations, human and robotic explorations. I go very quickly through them. So ISHA is set up of 23 member states. We are governed by a council to fulfill the requirements actually of all of our member states. We have something called a geographical return. So basically each member state expects to have a financial return back into its country relative to its contributions. We are spread over the whole of Europe. We have, I think, 7 centers and many offices. And I think this is very similar to India. It's just that we are less countries, less languages, so maybe a little bit easier than your situation. If you go now to the next slide. So I was wondering, space weather, what are the activities in ISHA on the space weather? And I'm going now clockwise through the individual pillars of ISHA. So starting with science, it's very clear that the main science questions of the sun are not solved, right? And I put a few in here. We are not able today to predict the solar weather properly. A lot of knowledge needs to be gained. I think this was mentioned before. This is the part of the science. If you then go to Earth observation, also on Earth observation, to understand what the impact and coupling of the solar wind to atmosphere and chemistry is an active part of the Earth observation projects. To the commercialization, industry and competitiveness, I come in a minute. Space safety, you heard earlier these days a presentation by Matt West, the project scientist of Vigil, so I'm not going into this, but the space safety area, where our space situational awareness and especially everything concerned to solar wind is handled there. the idea is to increase the number of sensors, right? The number of information sources. We do this by hosted payloads, which means whenever we have an opportunity to fly on any existing spacecraft sensor, we try to do this. The integration of the existing ground-based, maybe even space-based sensors which are there, to federate them together. Also, the idea is to have new small spacecrafts, also fleets of nanosatellites, and which are then providing a huge area of detectors. All of this has to come together in a data center. So here we have a federal activity going on, and I think you did this in lead of these activities there. Which is not an easy setup. We need many expert centers to support this activity, basically to get the knowledge in there. Then we go on to the technology. It's very clear, and at ISHA we have many activities ongoing to improve detectors, optics, also the modeling, it needs to be improved. To give you one example, there was a call for a European coronagraph out, because right now we are not really able to build internally occulted coronagraph. So there is a project out to do this. Then I'm coming operations. Here it's clear solar wind activity has an impact on operators. So if you fly spacecraft around Mercury, Venus, Mars, the Earth, you are interested in this. And human robotic exploration even more. If we're thinking about the space station, if we're thinking about our colleagues in the Artemis capsule right now, the space weather information is critical to human exploration that is coming up. All of this should give you a link if the question is, where could I have a chance in the future to find a job, right? All of this, it's very widespread. If I'm going from the left again, human robotic exploration, we need medical expertise, right? If we go to technology, we need material scientists. For the modeling, we need AI, IT specialists. For space safety, we need, of course, to build satellites, sensors, detectors, make them smaller and smaller again. Then I'm coming back to the commercialization. In ISHA, we have a lot of activities on commercialization. Right now, not too many on the frame or in the area of the space weather, but I expect that this will start very soon, that ISHA will encourage startup companies to get involved, build nanosatellites, build detectors, build sensors, provide algorithm, provide modeling, and so on and so on. And then back to science again, where it's important that we solve the physical questions behind to be able to predict the solar events, and with this actually activities on the Earth. Also would like to say, don't forget, in Europe, there are many, many other activities at the national or European level. And the EU called recently for an EU space weather activity, where ISHA is in the implementing role, but this will be an EU activity. And they clearly identified that knowledge is right now the key aspects which we have to improve. We have to improve the knowledge before we really can go and discuss further on space weather. And I think here I would like to stop.
Thank you, Joe. We have finally Karthik. Karthik, do you have a presentation, or would you like to just make a few remarks?
I have a few slides, but I think
No, go ahead. If you have a few slides, it's okay. And do not imagine that we're talking only about space weather. We would like to generalize this, because the jobs are not necessarily only in the field of space weather, but in the space industry, and you also represent the space industry in general. So if you have
so I think probably if I just speak off the cuff, it's probably more relevant than the few slides put together. So Thank you for inviting me to join this panel as well. I guess I'm a little out of place because I don't have a space weather background specifically, but I have been in the planetary science world and in academia for a while. I'm probably a good example of what can go right and what can go wrong when you're in academia. What can go right is the array of skills that you pick up, doing rigorous research, being able to self-manage research, but also collaborate with other people, build software, maybe hardware. There are some core skills that actually have a lot of value in the outside world, outside of academia. But the peril which I kind of suffered through myself, and I've seen a lot of other people go through as well, is that the PhD is a pretty hard slog for a lot of people. The idea of, becoming a specialist in one specific area, dedicating 3, 4, 5 years of your time, something that takes what feels to me as an extra special human skill. And what often happens, and what I've seen happen, not just with myself, but with other people, is that being curious, which is one of the things I think is a hallmark of engaging in academic research, means that your curiosities extend beyond just the academic world. And when that happens and you're working in academia for a while, it's possible that you start seeing other opportunities pop up and feel the desire to jump on them. That's kind of what happened in my case. So towards the end of my PhD, I noticed that there was something that I was interested in solving, a daily problem that I had in work that I was doing. I gathered a couple of friends to solve that problem, and 10 years later, we're now running a company. The company now works with a lot of space buyers and suppliers globally. And I'm a perennial PhD student, so I'm still trying to submit that last chapter of my thesis and finally get the title that I hopefully will be able to carry with pride soon. But what I think that in that story, and I'm happy to maybe as we dive into the questions detail a little bit more, I think it sort of presents the double-edged sword for people who are either in PhDs, in postdocs. You have what I consider a problem of abundance, which is you actually have a lot of opportunities, and figuring out what you want to do is maybe the harder thing than actually landing a job. And so, yeah, anyway, I'll maybe stop there, but I think that where I can chip in here is to kind of give you, from my perspective, some of the experiences I've had and where, particularly in the space world, there are opportunities for people coming out of the space weather community, but academia in general. There's actually a lot of opportunities out there. It's just sometimes being able to see through the forest to pick out those opportunities. Oh, and one very last thing I would say is, which is what I recommend to people. I tell people, do as I say, don't do as I do. So if you have an intention to finish a PhD or a postdoc, finish it before you go on to the next thing. And if I could tell myself, give myself any advice 10 years ago, it'd probably be that. So anyway.
Thank you, Karthik. Maybe I can just probe you on something you said. You said there are a lot of opportunities, and you just need to know what you need to do and just pick an opportunity that's suitable for you. Can I ask you to elaborate on that? What kind of opportunities sitting where you are? I know that you're just about to submit your PhD thesis. You have a company. If I make, you are pretty modest. You did not elaborate on your company, but I have known both you and your co-founder for some time now. So Sat Search is like the Amazon sort of the, they imagine themselves to be like the Amazon of the space sector, where they kind of manage the supply chain online, source products and connect that to people who need those products. That's correct, right?
Yeah.
Now, sitting where you are, what kind of opportunities do you see for somebody like you who's just submitted a PhD thesis or is a postdoc who's looking to transition into industry, let's say?
So I think this is only limited by your own perception of what you can and can't do. What I mean by that is, if you very narrowly decide that, the area that I have worked in during my PhD, during my postdoc, that is the only thing I will do, that is the only kind of job I want to continue doing that. It just so happens to be that a lot of fundamental science is limited by government funding. The government funding landscape right now is very dynamic globally. So in that sense, it might be hard to land your dream job. But in another sense, if you broaden your scope and you say, look, I don't necessarily have to stay within the specialist field I'm working in. I have a lot of areas that I'm interested in. What I've noticed, at least, is that academic rigor brings some very important and valuable skills in industry. One is the ability to take a question and break it down into sub-questions and build a rigorous framework within which you can then find a starting point to attack that problem. That is not as trivial as it seems. There are a lot of people who in academia are trained this way and yet don't necessarily see in that the ability to go and work in industry because they don't recognize that as a skill unto itself. So this is one example I give, is the ability to analyze problems, break down problems, build methodologies to tackle the problem bit by bit. That's a skill that actually stands you in good stead, I would say, across industry. It's not even just specifically the space sector. Within the space sector, for sure, this skill is important. And especially if you couple this with an affinity for space, whether it's specific areas of space or in general, with this kind of problem-solving mindset, I tell most people, like, look, this is what you need to understand about your academic experience, is it's much richer than the specific paper you published or the specific code you wrote or the specific presentation you gave at a conference. And if you can not limit your own imagination about where those skills can be applied, then I think basically the world is your oyster.
Okay, so I guess what you're trying to say is try to utilize your generic skills rather than trying to find a job in the specific domain of your research work. So along the same lines, if I can ask perhaps Amal, and you as well, Karthik, given your interactions with the space industry and both of you being part of the space industry, what are the kind of generic skills that you're typically looking for in a prospective hire? I know for Amal, this will possibly be somebody who has engineering or instrumentation skills, but if you have to generalize this to also people with good experience in electronics, software skills, could you just elaborate on those? What are you really looking for when you are looking to hire for your company as CEOs?
So Dibyento, as I've worn multiple hats, and I think it's always the same whether I'm looking to hire for my company or for as a PhD student. It's always the ability to learn. Is the student having the attitude of being able to tackle a new problem and find solutions? Are you going to be able to take a textbook and be able to learn how to solve it? And I think with how the world is changing rapidly right now, with AI, the learning curve is much, much steeper. I mean, you can get onto that curve very, very fast. So you expect somebody coming in to be able to get up to speed really fast. So I agree with what Karthik said about, like, if you have a problem solving skill set and it can be applied across a lot of domains, then the world is really your oyster. I completely agree with that. You can tackle a new problem. From my own background, I started on instrumentation. With UV instrumentation. I worked as a modeler at National Center for Atmospheric Research, which was basically incorporating data. I was an engineer with no background about atmospheric sciences. Right. So I had to look at, like, how does and I liked fluid flow. So I looked at atmospheric dynamics from a fluid flow perspective. And then I went into CubeSats and instrumentation, and so it spanned a variety of features where I was an engineer. I moved to sciences and then came back to engineering. So changing your domain field or needing to or wanting to stick on to what you think is your domain is not necessarily true. There are many aspects, especially if you go into space research and if you have an affinity for space in general, or if you like space in general, there are many areas that you work on. I look for the attitude of, like, are you able to tackle a new problem? That's the basic fundamental attitude that I look for.
Thank you. Do you want to add to that, Karthik?
Yeah, maybe I'll just say that the skills that there's a lot of skills that are getting commoditized right now. So coding is a good example, right? There are pretty good tools out there, these LLMs that can produce pretty robust code. So, and you can imagine 5 years from now, 10 years from now, they're only going to be better. So then the question becomes, what does the human operator of these tools need to be able to do? And I think that's when these other skills matter. These may be what are seemingly softer, and then sometimes people don't even really consider them skills, but they will turn out to be, I think, the most valuable. So being a very good communicator, both verbally and written, I think is paramount, right? Like it's going to make or break your career if you learn those skills, have those skills. Similarly, being a self-starter, right? An initiative taker, a self-starter, I think is going to also stand people in good stead. And then finally, being able to diagnose. So especially as we move into a world that's ever more complex with more and more connected systems, and we have, these AIs doing things that are not even fully traceable, having a mind to be able to quickly diagnose and understand, hey, what's going on here? Why is that happening? And being able to, in some sense, debug, not necessarily in the classical sense of code, but to debug problems in general, I think is a very valuable skill. So these are, funnily enough, some of the most important skills that I learned during the PhD. Although I had my topic of specialization in the science area, that was the reason I signed up to the PhD. What I was left with after is not necessarily just that knowledge, but a bunch of these skills. And I think that's what I recommend to people, is to recognize in them those skills, at what level they are, and where they can improve, and to use the resources that there are on the web, or meet people that they meet, to essentially continuously improve that set of skills.
Yeah, I think you touch upon this very important point that the PhD training is a very holistic training, in the sense that we learn to design a problem, write a code or analyze data to solve that problem, and then spend half our lives trying to figure out where is the problem in our code, right? And then be able to write, present, attract funds. And this is all skills that you think ideally any industry should value, right? But then there is this sort of lack of a breach where I guess in many countries, the industry is not really aware what an academic PhD entails, and that it kind of imbibes all these different set of skills. So along those lines, if you can come back to Judith and Joe, I think from the positions that you currently occupy, the key responsibilities that you have in terms of dealing with industrial partners, I think for Joe, being a program manager of a couple of different missions, you probably have had to work with industry partners, given that ISHA does lay a strong emphasis on collaboration with the industry, and rightly so. And Judith, from your perspective of dealing with multiple industries who are perhaps looking forward to having space weather intelligence, what do you think? And I'll go with Judith first and then come to Joe. What do you think they are looking for in students or postdocs that have this kind of a specialized training in space weather? Can you suggest even a few industries that are open to working with PhD students from academia? Judith, first.
I think this is a difficult question for me. So from the ISHA perspective, it's very competitive. So from the ISHA perspective, there is this ITT, so this open to tender. We all apply, and industry based on some requirements. Some of the requirements can be also as basic as being within Europe, so having a mailbox in Europe. And the skills, I think it's very open. So if the person is motivated, it can be as broad as AI, coding knowledge, management knowledge, also operational. So having just a machine being able to run day and night and have a service like that is already sometimes very needed. And then I think what is needed for the student and for anyone that wants to be involved, it's a network. We often forget this, but responding to such a big call, whether it's ISHA call, whether it's European call or international call, you need a network, because those call more and more, you cannot do it alone. You must team up with a multidisciplinary team. You need to team up. Often it's request that you have a full consortium. And so you need to be able to contact people to somehow be part of a consortium. Or if you want to run yourself your consortium, you need to be able to contact relevant people around you. And I think more than ever, we need to really team up and not anymore really compete to each other, but work together, share our data, share our knowledge, discuss during conference, so that we can write a proposal together. One of our latest proposal that we submitted to ISHA, we were just alone to propose it. So of course we won it. But the reason that we were alone to propose it, it's because it was a huge proposal and we basically had half of Europe involved in. So of course, I mean, it's one proposal, but it's basically everyone on the market, everyone who is capable to work on it, everyone. And at the same time, we did not have many choice. We had to do it like that because it was so big and it requested so many different aspects that it's becoming really multidisciplinary work. And therefore, we need a bit of everyone. We need a student ready to jump on it. We need industry with all their skills. We need a manager. We need coordinator, IT infrastructure, etc. The difficulty to what is the skills for a person in terms of career strategy. It's a bit difficult for me to respond to this. I would need to think in terms of career strategy, but yeah.
Joe, would you like to make a few remarks on having worked with perhaps some industries and what kind of people they're looking for, and what are typical industries that look for PhDs with skills that we generally tend to have?
Let me deviate first a little bit. There was a question in the chat on how ISHA is recruiting. So yes, indeed. If for ISHA staff, we require that you have a passport from a member state. So that's clear. However, we have also a lot of contracting staff working here, which are hired in from companies. And there we do not have any constraints on this. So there are possibilities. Let's say we also had many recruitments open in the agency here for the last years. So in ISHA, we are typically looking for middle-aged, experienced engineers and scientists. Our problem here at the agency is that we talk to industry, and if we want that they take us serious with our requirements and that our requirements are feasible and realistic, you expect already a good level of work experience. So we're recruiting a lot of people above 35 to 45, right, which coming with expertise. Also from us, I think you expect from an ISHA staff that whatever the problem is that might be there. And as a project scientist, I can tell you I'm looking from the electronics over to the AOCS, over to the antenna allocations, to what you have to quickly dig into and maybe asking colleagues who know better, but can quickly dig into a topic, kind of handle it properly and come to an opinion and which you can defend. Now on the industry, I think you did mention this before. We of course expect from industry to have the specific knowledge on the topic, and this is going really widespread, actually, from electronics, mechanical, optical, medical, nanotechnology, detector technology, and so on and so on. However, as you did manage, this goes together into a pack, and it's getting more and more important that somebody is able to manage these. And this is not trivial. Management capabilities, management abilities are kind of rare. So also there, my advice to students is if you can get somehow in your project this kind of expertise, try to get it. I'm not sure if you're taught at university kind of manage a small team or so, but what does it mean, right? How do you specify requirements? How do you test them? What is the language that we speak in space industry? So this is quite important. And you might be a freak in your niche, but you might not be able to work in a team together. So this is very important that you are team capable, right? You have the expertise. You are open actually to learn whatever is needed from you. I think Kartik mentioned this. So be open for everything what is coming. Also, I would like to manage something, probably this is the wrong audience here, but at the agency, we need a lot of contract officers. We need a lot of lawyers. There are a lot of legal issues with this. So we are recruiting, a lot of them. And I think also the industry, they need even lawyers, right? We have contracts and sometimes I don't understand what we write in the contracts. I have to go to our contract officer to tell me, right, change this or be aware what it means. So I think the area is widespread. Be open to this. And basically, I think my advice to the younger generation is try to do what you like to do, right? You will find a spot, don't worry. But don't go for a job because it's paying good or something like this. No. Do what you like to do, right? Be open, but do what you like to do.
Thank you, Joe. I mean, this is of course an option that all of us would like to have. Just do the job that you would love to do. But in a world which is getting highly competitive, sometimes you don't have that choice, and so it's important to also go beyond and explore other opportunities. So in that context, if I can ask a difficult question to both Amal and Karthik, and I would like you to be very honest. Where do you think people like me, who was a professor, academicians fail in terms of imparting a certain skill or a training to students that is highly desirable in the industry sector? So in other words, what do you wish that PhD students could bring to the table that is not part of their training, which they could in principle then separately upskill themselves in? Who wants to go first?
Yeah, I can chip in. I think maybe Amal's
Sure.
probably got a more precise answer than I do. But look, I think this is maybe almost a philosophical question, because at some level you can ask
We
the
are all
question
philosophers
whether
at some level, right? So it's okay.
No, so I mean, I would question whether it is your job as professor to do that. I think, you have
I
your
mean,
core skill set,
to be quite frank, nowadays I think so, because I did a very simple calculation. Let's say I'm producing this many number of students in India, and in 5 years, let's say I produce some X number of students, and I look at how many positions gets open in the field in 5 years. And then what I find is, out of, let's say, 10 students I produce, maybe 3 will get a permanent job as a faculty. And so this is a difficult number to grapple with. So I would actually like my own students to have the skills that can allow them to transition either to academia or to industry. I think this
but
is a real issue.
I would say the skills training is probably not where I see the need for that. I don't know whether what you
Well, I'm not saying it's my job, but the knowledge is something that will help us, and also the students.
What I
So
was
if you
going to
have
say
that
is what you
knowledge, give us that knowledge.
What I was going to say is what you just summarized about the truth of the world. I think that's what students need to hear. I'm not sure that you need to teach them skill X, Y, or Z, but the truth of the statistics that you mentioned, right? That out of 10 students that I'm going to have and graduate, only 3 of them will get a position in this industry. 7 of you are going to have to look elsewhere. So you better start early thinking about what other interests you have, what skills you need. I think that's maybe the more important thing to share with them than a specific skill. I don't think you need to teach them how to code in Python, or I don't know if you need to teach them
But
how to solve
they do learn how to code in Python. I mean, they're very good at this, actually. Surprisingly, the students now are really good in coding in Python. I think we can all very confidently say that most students who are attending the symposium are probably very good coders in Python.
But that's what I'm saying. So I don't think any of those specific skills are things that you should be focused on teaching them. I think giving them a perspective that they have to be aware of the career path options that they have, and that, yeah, in a very narrow sense, if they want to do the very specific thing they have interest in and get a faculty position in that, that might be hard. And my suspicion is many students don't hear that enough, which means that they hit the end of the PhD program, and that's their expectation, that they're going to get that job as chief scientist at NOAA or whatever it is. Instead, I think coaching them through the process to say, look, that is one possibility, but it's possible that you're not going to land that. So widen your horizons and think about what other interests you have, and think about what are the skills to get into those areas. That's what I would say. Is I don't think it's a skills issue. I think it's more a mindset coaching issue and a confronting people with reality that there are only so many jobs for space weather scientists in the world. That just happens to be the case. So maybe that's not a satisfying answer, but
yeah, that's okay. I think give us a sense. I mean, you really sidestepped the question a little bit, but I think at least people like us know our roles in the sense that it's our job to make it clear to them that everybody's not going to end up in academia. Anybody wants to add anything before you open it up to other questions?
I'd like to just chime in. I agree with Karthik. I think it's very true. Not everybody's going to get a job in academia, and sometimes it's good in the US, especially these days. It's good. It's a good thing. Industry pays a lot more. Judith actually mentioned in her opening slides that we need people in the industry who understand space physics, because a lot of times industry comes with not a good knowledge of the problem they're trying to solve. Some of it is communication from the agency of giving what they need to build, but having hired one of your PhD students as my program manager also, Divyendu, let me answer your question.
That's right.
PhD students are very much focused on solving one problem at a time, and when you go into industry, that's not the case, right? You're working on multiple projects. You need to be able to divide your time between projects as well. So the whole aspect of devoting all of your time into the solution of one big problem mindset needs to change a little bit if you're taking up an industry job. You need to be able to manage your time. You need to be able to prioritize your time for tackling multiple projects. So when I hire a PhD, I'm not looking at a PhD coming in at a starting engineer position, right, or a starting scientist position. It's more of a leadership role. It's more of driving requirements. And companies like mine, we have very few people, and we need people to be able to tackle multiple problems. So having that mindset is actually a good thing to kind of add on to you, when you're doing a PhD. So I'll just leave it at that.
Thank you, Amal. I will now open this up to the audience, and if the audience has any questions, I see that there are a lot of questions in the chat box. If somebody wants to pick up some of the questions, you can just go ahead and answer. On the other hand, I would love some audience members to, if you have a pressing question, which is related directly to the panel, not something that's a very personal, individual question, but related to the panel discussion. Please feel free to raise your hands and ask that question. And this includes the organizers as well. I mean, you folks are also PhD students and postdocs, so feel free to raise your hands and ask questions. Go ahead and unmute and just ask questions. Would love to hear from all of you.
I see some questions in the chat.
Mayank, yeah, you can go ahead. Pratik, you can go ahead and just ask some of those questions while people are warming up to ask their own questions themselves. Pratik, you can just...
Sure. So Aswin asked this. I think we have already covered this. What are the major skill sets needed to be a space weather analyst in industry? Also, what are the requirements to be one?
Judith, do you want to discuss that a little bit? You want to have a quick answer to that?
So to be a space weather analyst, I think, if you are a PhD student, I really like what was said before is you have a very narrow knowledge on a very narrow event or mechanism, etc. And what I could propose is actually within the Rail Observatory, we provide training which allow you to a little bit step back and have the full chain of elements. So while doing your PhD, you specialize in one specific things. which are crucial in one specific modeling, etc., or one specific scientific question. Here, it's giving you the opportunity to put the U element, what you have learned, in the full chain mechanism from sun to earth, from sun to planetary, etc. And this is, I can put it in the chat, is the space weather training. You can register this online. You can access. Because I think what you need to be as a space weather analysis, and especially when you are on the side of the industry, they don't want to hear about the whether how the coronal the mechanism of the coronal heating. Of course, it's too complex. They don't want to understand what is magnetic reconnection, what is the mechanism of a CME and a flare, whether the coronal hole size has an influence and how much. They really want to hear the story, what's going on the sun and why is it relevant for the industry, and how and what will it impact. And therefore, you need to step back a little bit and see all the connection between all the elements, between solar physics, heliosphere, magnetosphere, ionosphere, and then go to the industry and ask, yeah, well, what are you using? Which mechanism? Why are you interested? And tell them and explain them how space weather is relevant to it. So I think this is some knowledge that if a PhD postdoc or whoever comes from our field would need to take this step back. I can give you this this link to see the courses, but of course you have books, you have plenty of literature. Huh? This is just an example. Yeah, I will put it in the chat. No, that's
All right.
Yeah.
Thank you, Judith. Do you want to continue, or you're sort of done with your answer?
No, I'm done. I mean, unless you have
So
further comments.
I have a question which is meant for Karthik from Shilpi Bhuni. I think it's a very relevant question. Shilpi, are you around? Are you online? If you are, then you can ask it yourself, or I can ask it on your behalf.
Hi. So thanks.
Go ahead, Shilpi.
Yes. So actually, I think Karthik already gave an answer. So my question was that, because I'm very curious right now,
The
like what
universal
kind.
website question. I am also interested in an answer to that. So you may go ahead and ask the universal website question that you have.
Yeah, no, I was kind of curious. I'm kind of curious about what kind of jobs are there in the industry, like space industry. So it's very confusing to like, going to first getting to know the company and then go to the company website and see the jobs. So if there is any kind of website to look for jobs in space industry. So I think Karthik already gave a answer on that, that there are already some websites. So thanks for that.
Okay, all right.
Yeah, maybe
Karthik,
I'll just add what I had put in the chat as my answer.
Yeah, maybe you can just
there are plenty of websites. I listed 3 of them there. There are many more websites that you can find. But I would suggest tackling this job search problem as not a website problem or like a looking for vacancy problem. In my case, bar one position, I have never gotten anything by applying through the front door. The way I have gotten it is by building relationships with people, genuine relationships that lead to people seeing an opportunity, wanting to work with you. And then look, later in your career, sometimes it flips. Sometimes you become the person who can offer somebody else an opportunity. So all of that comes down to the bottom line of, I think, this thing that when I was in university felt like a bad word, like networking, right? It sounds like something that engineers and scientists don't do, shouldn't do. But the truth of the matter is, it's maybe the most important soft skill because it's really about building relationships. Nobody launches a space mission on their own. Nobody operates a space weather service on their own. Very few people these days publish papers completely on their own. So knowing that you need other people means that I think the emphasis that I would put on is find opportunities to meet people. And the way that I've done this in the past is it can be as simple as you reach out to somebody on LinkedIn that you're interested in having a chat with, and you invite them for a coffee chat, maybe a virtual chat, but you need to give them a reason for it. And the one reason that I think I've seen people go to, which doesn't really work, is because you want that person to give you something, right? Like people don't like being demanded of. So if you approach somebody with a genuine interest in what they're doing, maybe something to offer them and a desire to chat with them, in that mode, I've found lots of people are open to talking to you. And when you build those relationships, that's how I found actually the hack to finding a job in the industry, less than applying officially.
All right. Thank you. I think we're running out of time. Pratik and Ketaki, can you tell us, should we now close the session here? I know that you have a talk following up.
I think Laura is not here yet.
Okay, so maybe we can take a couple of other questions. I see a lot of questions that are not relevant to the session. They're very technical questions about space weather and instrumentation and things like that, which I'm going to ignore. I'm going to still stick to the theme of this panel, which is the industry academia panel. So I'm going to search for anything that is new.
Sorry to interrupt.
Yeah, sure.
Laura just messaged that she is here.
She's here. Okay,
maybe we
great.
can
So I
wrap it up
think then
in
we should
5 minutes.
probably close up. All right. Well, thank you very much to each of you. I think this panel is a beautiful example of international collaboration and international friendship. I see people from Europe here, Europeans from Europe, and an Indian in Europe, and an Indian in the US, all put together. And from academia, we have Karthik, who's actually chugging through his PhD while running a company as well, and then Amal. When he went through all the motions, he was also in Singapore as a professor. Then he moved back to the US, and then he opened a company and is still working at LASP. Joe, who is a great friend, has made a couple of trips to India and we've become very close. Value his friendship. Judith, whom I know for a while, but I think we meet for the first time online. A pleasure to meet you again. And thank you again for all your time. And I hope that this discussion is not the last discussion and it will continue. And we and the students and the postdocs that are here can get to see you and work with you in the future. With that, I will close and good luck to all of you. Thank you.
Thank you very much.
Thank you.
Bye-bye. Thank you.
Bye. Namaste.
Thank you. Thank you for all the panelists and our moderator. Thank you so much. And now we move forward with our invited talk, which will be given by Laura Hayes. It will be about SunPy. So I'll first introduce Laura. Dr. Laura Hayes is a Royal Society Research Ireland University Research Fellow and Assistant Professor at Dublin Institute for Advanced Studies, based at Dunsink Observatory in Ireland. Her research focuses on solar flares and space weather, particularly using observation from missions such as Solar Orbiter. She plays a leadership role in heliophysics software development and community infrastructure through the SunPy project, and she will be talking about that only. So I will give the floor to Laura.
Great, thank you so much, Becky. And I apologize for if I run that discussion short. It was really interesting. I only came in at the end there, but lots of very interesting discussions. Can you see my screen okay?
Yes, we can see.
Yes, great. So what I'm going to talk about today, as Keki mentioned, is the SunPy ecosystem. So kind of give an overview of the SunPy ecosystem for doing solar physics research, where it's kind of come from, where it's going, and how you can kind of get involved. So this talk will be kind of an overview talk, and hopefully we have some time for discussion at the end. As Keki said, I'm not funded by SunPy. I am a solar physics researcher, but just over the years, I've gotten more and more involved in open source software development, and now kind of helping to lead some of this role within the SunPy ecosystem as it's grown to be. A few years ago, Python was kind of taking off. We were still very much in an IDL world, but now we're in this time where everything we do, most of it in solar physics, is now through SunPy. So how do we build a sustainable ecosystem that works continuously for reproducible science, which is really important for what we do, but also for thinking to the future for new missions for things like space weather. We know now that companies are starting to use SunPy for doing space weather type of things, and how can we make sure that this ecosystem is sustainable going forward? So just a bit of a motivation about why we need a whole ecosystem, right? And why do we need an interoperable software system? A lot of us as scientists, right, you basically want your code to do some analysis so that you can get your science out, right? So a lot of us write our own little routines that we do to make plots, to find diagnostics. But we really want to be able to now use data from lots of different observatories to answer some of the big science questions that we have, especially in solar and heliophysics, right? We're living in this golden age where we have lots of missions, both in space and on the ground, that's looking at the sun from many, many different perspectives. So if we even just think about the diverse data that we now have from an observational point of view, we have both remote sensing instruments, so taking images of the sun at a distance, looking at the light from the sun, for example, images of the sun like AIA or remote sensing observations. And then we also have lots of in situ instruments taking measurements. So this is instruments on spacecraft that are measuring things like magnetic field and solar wind and energetic particles. These are measuring the conditions of the heliosphere at the spacecraft. So already we have kind of diverse data around these 2 points. We now also live in a world of multi-messenger observatories, right? Where you now have Solar Orbiter and Parker Solar Probe, which are orbiting the sun at very different viewpoints that we have from Earth, right? So we're kind of seeing different perspectives of the sun, and how do we use observations we see from one perspective and then combine that from another perspective to do interesting new science. So this, of course, is kind of another element of adding diverse data. We also think we have data from planetary missions, right? So maybe instruments like or missions like Bepi-Colombo are measuring things like the solar wind. They also have a suite of instruments on board that can be used for solar physics. So these again have different data formats for maybe working with in the planetary community. But as solar and heliophysicists, we can actually use a lot of this data to do some new science. So again, another kind of challenge in terms of different types of data products. We also run a lot of coordinated campaigns, specifically I work mainly on Solar Orbiter. A lot of the time we're pointing at the sun from a specific viewpoint, and we want to make sure that some satellites from Earth or ground-based observatories are pointing at the same target. And then if we're trying to combine that data, that becomes a challenge not just from data formats, but from like a coordinate transformation perspective. So in terms of a scientist, what you kind of want to do is you want some magical package that you import it. You say, get me all the data between these 2 time ranges or of this specific event, analyze all this data, and write your paper, right? Maybe that's a bit of a joke, but the idea is you want to be able to do this all in one workflow. You don't want to have a load of codes to get data from one instrument that then is in a different language to combine it with a different instrument. And this is kind of the motivation, I guess, for SunPy and for an interoperable software ecosystem. We want to be able to have codes that work very well with each other, so we can work first of all with each other. As scientists, we can compare codes, and then we can also work between instruments. And we're taking away, I guess, we're abstracting away some of the complications that is taking up a lot of scientists' time, where you really just want to get to your data and work with your data. So you want to be able to play with high-level quality data and then expand out into the ecosystem of Python that we have in terms of packages that are already available. So not reinventing the wheel and writing all of these new codes. So I guess that's kind of the motivation of the SunPy project. And I guess a lot of things I'll be talking about, we use SunPy is also the package, but it's also much larger than that. By definition, the SunPy project is actually a community of scientists and software developers. It's people, right, that are trying to create this ecosystem of Python packages. So several packages there, right? So we're not just the core package, but other affiliated packages. And we develop not this core, but also the range of affiliated. So in terms of what the project looks like, we have the code, of course, right? So we have our core package, we have our affiliated packages. We also have people, so the people behind the SunPy ecosystem, whether they be developing the code, maintaining the code, community roles for maintaining the website, our lead developer and things like that. We have people who contribute, who are not necessarily work on SunPy a lot, but maybe swing by, they report a bug, or they say a little bit of code. And then, of course, users. If you use SunPy, you are part of the SunPy community. And this wider community involves several things, right? So we have SunPy community meetings, we have weekly meetings, we usually have a yearly coordination meeting. We also are more and more now becoming kind of making sure we kind of have a presence at different solar conferences. Maybe we have a small session or we have kind of coffee breaks so that people can come and ask questions. And then we also have things where we do summer schools, and we're also quite involved with Google Summer of Code, where students can come and kind of work with us for a few months. And I thought I'd maybe, people maybe don't necessarily know the kind of history of SunPy. So here's kind of a brief history. So the concept of SunPy actually started in 2010, which is actually a good few years ago now. And if we think back even back then, Python was really kind of starting to get popular, right? It was kind of getting going, this open source software development. and the fact you have kind of this free software, which is very different from proprietary softwares like IDL, for which most of solar physics was done in. So this was the idea to kind of start, well, Python is getting popular. Maybe we need to write some routines that we can kind of use solar data within Python. In 2011, it kind of really started, and most of it started actually at NASA Goddard Space Flight Center. That just is based on some people that were there, such as Steve Chris and Jack Ireland, and Albert Shi. So that's kind of the beginning of it, starting again in this very early Python world. In 2011, version 0.1 was released. So this is a really, really early stage of SunPy. There was very, very basic stuff you could do, but it was our first kind of actual little release that happened. In 2015, we had version 0.5, so still not version 1 yet, but we're the first SunPy paper that was published, trying to just discuss about kind of the needs of a solar physicist for using Python and why SunPy kind of comes into this. We had a massive milestone then in 2019 where we actually released the first version 1, and this was very, very different to the previous versions. If we actually look at the commit history from then, it was a lot changed during that time, and we actually published our first real kind of scientific paper in the Astrophysical Journal describing the version 0.1. And where we are now is we're on version 7.1, and it's not just a SunPy package, it's now a range of affiliated packages, and we kind of really are at a point now where you can do most things you might need to do for solar physics research in Python. Of course, there's a huge amount of legacy code in IDL, and we're not code bashing here. A lot of us are still bilingual, if you like. We'd like to get to a point where you can kind of do everything in Python, but it's really come a huge leaps and bounds since it first began in 2010. And that kind of aligns also with the development of Python throughout the years. If you go back and look at what Python was like or the other packages that we might use back in 2010, it was a very, very different world. So I always think this is nice to kind of get a history, and it is just people who are scientists developing Python code to do their analysis and putting it into this ecosystem. These are some plots showing you kind of the development of SunPy, right? So the first plot here shows merged pull requests. We do everything on GitHub, which I'll talk a bit about. But we can see the number of unique contributors is 1 or 2, right? So we really, for a healthy package, we really want to kind of grow this. We want to make sure that there's kind of more users contributing to SunPy. You can also see here, these are all the number of merged pull requests. So you can see this was kind of around 2019 when we had the merging of version 1. It almost looks like a solar cycle, but an anti-solar cycle. That's not related, but it's kind of interesting to see how the development has changed over the years. And you can see as we're kind of coming, as it's becoming more of a stable package, we don't have as much larger changes because we can't go and completely change SunPy now because a lot of people depend on it. So it's things about how you kind of maintain the packages or the software now as it's at a more of a mature stage. Again, this was our paper that we published in 2019 for our first version release. And we actually have over 400 citations. And we know that a lot of people are not maybe necessarily citing SunPy in their papers. If you use SunPy in your papers, it'd be really great to cite it because it's very nice to know and track kind of what SunPy is able to do for your science. So where does SunPy sit within the larger ecosystem, right? So I've kind of drawn these circles here. SunPy lives in this kind of bubble of solar physicists, developers. It sits within a larger AstroPy community or astrophysics community. And then even within that, it fits larger within the solar and heliophysics community. There's also another community which SunPy is one of the core members, it's Python and heliophysics. So other packages that might work on magnetospheric science, for example, we kind of are trying to aim forwards in the future that maybe SunPy can really work well with those packages too. And then outside of this, of course, then SunPy gives you a way into using other communities, right? So whether you're using SunPy to read into your data to get it into a Python environment and then use different packages like scikit-learn or whatever you might use, and how we depend on each of these. Now, I'm just going to take a step back and say, okay, well, what is SunPy core? This is one element of the SunPy project, but what are the main components of that core package? There are kind of 3 main components, and the idea is that the SunPy core package is generic and not specific, right? So this is where we have all our base things you might need to do solar physics. And then on top of that, we build our affiliated packages. So our main components consist of data download. So we have a unified data downloader called Fido. And the methodology behind this is that whether you get your data from the VSO, the Virtual Solar Observatory, or from NOAA, or from JSOC, or from some FTP sites, From a user point of view, you can just do fido.search, give it a time range, give it a wavelength, give it an instrument, and you return that data. So we're abstracting away where you can get your data. So in kind of a unified way, you can look in lots of different places and get your data. And this is kind of written within SunPy core. This is also extendable. For example, we extend this to hook in now to ISHA archives. We can get solar orbiter data, for example. So data download is one of the main components. The next main component is data containers, generic data containers. And our two main ones that we have are MAP. So this is two-dimensional data arrays with an associated coordinate framework. So the world coordinate system is what we use. So data container for holding that type of data, and then data container for holding time series. So measurements is a function of time that consists of metadata and units and all of that. So that's our second kind of main component that's within the SunPy core package. And then maybe our most powerful kind of functionality that we really provide is our coordinate framework. And this builds heavily on the AstroPy coordinate framework. Again, not trying to reinvent the wheel, but again, making this interoperable ecosystem. And this is becoming more and more important when we're doing multi-messenger science, right? So we're looking at the sun from different perspectives and how do you combine these? And I'm sure many of you have used it. Many of you maybe have banged your head against the wall trying to use it. And we're trying to make that a little bit better. But I know coordinate transformations themselves are quite a challenging task. So I'm just going to talk through these different components and then talk about then how we can extend that into our affiliated packages. So our data search and download, I'm sure many of you have used this before. The idea is that we have this one API for which you can look for data from different sources. So again, we have many different engines that we plug into. It's also extendable. So we have the SunPy affiliated package, SunPy SOAR, which uses the same framework to look for solar orbiter data. And if you serve your own data, you can write your own FIDO client within SunPy. So for example, maybe we're discuss like at ETL 1, maybe someday we'll be able to be searchable through FIDO. So we're kind of working with different instrument teams to maybe help how this can be kind of extended to new data sources that come online. Then once you get your data, our different data containers. So our main one, maybe from looking at a time series perspective, is called time series. And this is a data container that can hold information from different files. And it supports many different files, and we have lots of different sources we support. We can also increase this, so we can add more if people have interest, and this is where we need community feedback. But the idea is that you can pass different files in. You don't even necessarily need to tell it what file it is. It will understand what file it is based on reading it, and then kind of contain that units and the metadata, which is really important for doing science or if you're doing any operations on that data. And again, this can be extended not even just within SunPy, but also to our affiliated packages. An example of this is StixPy, which is an affiliated package for working with Stix data, which is an instrument on board Solar Orbiter, which again can read in Stix data products. And then when you have something in a time series, it works the same way, regardless of what data is underneath there. And then our other one is MAP. So as I mentioned, coordinate aware 2D images. The key thing here is that it has a standard WCS, a world coordinate system from the FITS standard of WCS. So you can pass it a file similar to time series. You don't need to tell it that it's an AIA file or the LASCO map or anything. Once it is a FITS file that has a standard FITS WCS, you can read it into a SunPy map, and then you're kind of opening the door to all the operations you might need to do, whether it be for cropping, for reprojecting, or for kind of putting maps on top of each other or extracting that data out. And then finally, our coordinates framework, as I said, is really quite powerful and really good for representing and transforming coordinates in solar physics. This kind of crazy spaghetti plot is a way in which we kind of hook onto the AstroPy framework and extend it outwards. So all of these, this is just a way of how we do the coordinate transformations between each different frame. You don't even necessarily need to know this. It's just to highlight how complicated it usually is to do this, but with SunPy we can abstract that away. So the blue ones here are the AstroPy frames, and the white ones are the ones that we've written in SunPy that live within the SunPy package for doing different coordinate transformations. So for example, if you have a helioprojected frame and you want to, or a helioprojected map, within one line of code, you can actually reproject it to a Carrington map. So again, it makes it really, really easy to do these kind of transformations that you might need to do. And as I said, this is really important for now this multi-messenger science that we're now being able to do with Solar Orbiter. So for example, on the left-hand side here, this is a Solar Orbiter EUI image. So when Solar Orbiter was at around 90-degree separation from Earth. And again, literally within like 2 lines of code, you can reproject it to what that sun would look like from an Earth view. So again, it makes it easy to do these transformations and as a scientist, get to the data that you actually really want to play with. You can also do lots of other fun things. You can plug into JPL Horizons and you can get the positions of lots of different things in space. So this is just an example of taking a LASCO field of view and trying to find all the stars or planets within that field of view and plotting them on top. And you can also do wonderful and wacky things. This is an example of a 3D sun when we had times when SDO and the two stereo spacecraft were looking at different perspectives, and we can actually really see a whole 3D sun. So again, sometimes these coordinate frameworks and map together in a unified way. It doesn't necessarily matter where your data is coming from. Even as a user, you don't even need to necessarily know the positions of your spacecraft. It's all taken into account within this framework. And that's great. So we have our SunPy core. The idea of all the code that lives within SunPy core is kind of generic code, right? So it's not specific for prepping a specific type of data product for a specific thing. Maybe a lot of people aren't using that data product. So that might live outside of SunPy, but work very well within the SunPy core ecosystem. And this is where the idea of an affiliated package comes in. And the reason is that we have these affiliated packages is that we can keep SunPy core as kind of a maintained bubble that's generic, and then outside we can easily change lots of different things without disrupting kind of the main package. So these affiliated packages are well-maintained open source packages that build upon or extend the functionality of the core SunPy library. And they don't necessarily need to be maintained or run by people that are developing SunPy. The idea is like, for example, lots of instrument teams develop their own affiliated package. We just have a set of criteria for it to be listed on our website as an affiliated package. And just some examples of what our affiliated package ecosystem looks like. We have NDQ, which is a package for working with n-dimensional data with WCS. And this is again is kind of a more underlying package, which we will depend on more and more. But this is just maybe so you've heard of it before, but it's a really, really powerful package. We also have SunPy Soar, as I mentioned. So this is a Solar Orbiter archive plugin for FIDO. So this is an affiliated package of SunPy. An example of this is right. So you might ask, well, why isn't the Solar Orbiter archive within SunPy Core? And the way we kind of developed it as an affiliated package, we were able to iterate on it quickly. And then someday we might actually put that into core. So it's kind of a way that you can kind of have this incubator of playing around with working with a package, and then it might get eaten up into SunPy in the future. But at the moment, it is a SunPy affiliated package. We also have SunKit Instruments and SunKit Image. So these are two other affiliated packages. SunKit Instruments are places where some instruments don't have enough codes to really, develop a whole new package. Maybe there's only one or two codes. This might live in SunKit Instruments that are really specific to certain missions. And then SunKit Image is a way for working with, we have lots of different data processing techniques in there for doing image processing. So for example, the WOW algorithm, it lives in there. We also have ways you can kind of track things. So that's kind of another one of our affiliated packages. I also have DKIST Pi. That's an affiliated package of SunPy. It's actually heavily developed by our lead developer of SunPy. But again, it lives on its own. It is completely maintained by the instrument team, but it just integrates extremely nicely with the SunPy ecosystem. So, for example, you can use FIDO to find data. It reads it into maps, etc., etc. Also, AIA Pi is another example of an affiliated package that's an instrument specific. So again, if you want to do AIA prep, or do some deconvolution, that lives within AIA Pi, uses SunPy maps for example. We also have SunKit MagX, which used to be called PFSS Pi for doing PFSS extrapolations. And then other little ones like this is called RunGen. This is for looking at X-ray processes on the sun. So our review process to become an affiliated package, there's kind of some criteria that we set. So you might want to develop your own. It works well with SunPy, and then we go through this review process to actually become an affiliated package. And if anybody's interested, please go check out our affiliated descriptions on our webpage. And how does this whole then ecosystem work together, right? So this is the ecosystem. We have SunPy Core, and then we have these affiliated packages. And how do they work together? So this is an example of looking at the sun from three different perspectives, from stereo A, from SDO, and from solar orbiter. So you can see the three different positions here. We have a HMI synoptic map, and then say we want to see these different perspectives, do an extrapolation, and then plot what that extrapolation looks like from the different viewpoints. So in terms of the packages that we used SunPy to get the data, to get the HMI synoptic map, to get the SDO data. We use SunPy Soar to get the solar orbiter data. We use AIA Pi to prep the SDO map. We used, map, again, that's within SunPy Core. We use SunKit MagX to then do the extrapolation, and then we use the sky coordinate framework to then plot what that extrapolation looks like from the different perspectives. So I guess this is just one example of how these things all work together in a seamless manner. And if you're interested in more of the concept of this, we published a paper in 2024. That's not a technical paper, but more of the idea behind driving this SunPy interoperable ecosystem. And this is just a QR code to that paper. But again, just to sometimes it's confusing about how the SunPy kind of works as a whole. And I think this paper kind of tries to put into the whole concept behind the way it has been developed and continues to develop. And this really enables multi-mission science, right? So again, thinking back to our core data product, we have a unified way to get your data, regardless of where you're getting it from. We have shared data containers, whether it be map or time series. We also have NDCube, which is a way to do mission agnostic data analysis. So if you have an n-dimensional cube in a WCS, you can easily read it in, and it works well with SunPy. We do coordinate handling very well. We now can support SPICE kernels. So this is important for really specific tracking of where a spacecraft is. And we're kind of really doing these cross-mission workflows, and we're trying to do more and more example galleries and more examples of how you can do a lot of the things you need to do within SunPy. A lot of the time, and this is something where it really is a call to everyone here, is someone's like, well, SunPy can't do this. And it can, it's just we don't have an example. It's a matter of kind of understanding what is available and how you can actually use it for what you want to be able to do. If you're interested, I'm sure many of you have seen it before, we have quite an extended documentation, which can always be improved. So if you go to our documentation on our website, we have kind of this tutorial for new users. We also have specific how-to guides, which are not even, not just example galleries, but kind of more specific tasks with SunPy or snippets of code or even kind of conceptual solar physics things that you kind of need to understand to be able to use it within SunPy. We have topic guides. So for example, trying to understand the why of the way things are done, maybe in SunPy or just in general for solar physics. And then we have our code reference. So if you're interested in what a specific function does, you can go to our reference and kind of see the actual code documentation or doc strings. I think most powerful, and I use this a lot, even though I'm heavily, know SunPy quite well, is our example gallery. So we have quite an extended example gallery of how to use the different operations within SunPy. If you click into one of these, you have a full example in Python code, which you can download as a Python script or as a Jupyter notebook. I also want to mention that this example gallery is specific to the SunPy core website or SunPy core package. But if you click on the documentation tab here, you can actually see all of our affiliated packages. And if you click into one of these, it brings you then to the specific documentation of that affiliated package. And then you can go, for example, and then see the example gallery of NDCube. And one of the operations we're kind of working on over the next while is to try then integrate these to all be able to be searchable. Not that you necessarily need to know not what affiliated package you need, but you can kind of search it depending on what you're actually trying to do. How is SunPy developed? Okay, so SunPy is not just an open source project and that our code is open source. It's actually an openly developed project. So all the development decisions, road mapping is all done online and openly. So anybody can go and see what we're discussing or what pull requests are done, or you can review the code or you can make a suggestion. And we manage this all through GitHub. This is a screenshot from our GitHub webpage. So within that GitHub project, we have the SunPy core package, which you can see. We also have lots of other packages, or kind of repositories. For example, our website is also developed online, and everything is centralized around this GitHub. But how does it actually work in terms of adding things to SunPy, to making decisions, to reviewing code? This is again all through this open development workflow. So as I said, everything's developed publicly. All contributors, whether you are a main SunPy developer, whether you're the lead developer or you're a newcomer, you all follow the same workflow. And several things is like writing code for software like this is maybe slightly different to writing code for your own analysis. So that's something to maybe, it's a bit of a learning curve, and we have kind of ways we try to enforce kind of a code style and writing tests to make sure that the code that you're providing works. But we really would love contributions from everyone. And we need to have kind of this objective system of reviewing and testing to kind of ensure code quality, reproducibility, and long-term sustainability. And on GitHub, how do we ensure that a code has a certain quality, right? This is all done through code review. So if you have some code you want to provide to SunPy or update or fix a bug. You kind of make a pull request on the GitHub webpage. New code needs to be within scope. Does it actually useful for a solar physics workflow? And we also would ask people to write new tests and documentation. We have lots of ways to do this in terms of for formatting. We have automated formatting and linting tools. So when you make a pull request, all of these things are checked. And I think really importantly is we also have this continuous integration and development tests that are run automatically. So if you apply a new piece of code, it will run all the tests of all the other code to make sure that's not going to break something. And this is really important as, again, as I said, the sustainability of this code, and you don't want the SunPy to break every time you kind of you try to update it. So this is kind of the powerful, modern workflow for developing software in this way. And what does the governance of SunPy really look like? We actually changed our governance last year. So while we're a community, right, we need to have some kind of structure in terms of how we decide things or how we kind of look forward, or maybe how we think about the sustainability, or we're making big decisions. Like say, for example, we wanted to decide it as a community, we don't need MAP anymore. Let's get rid of that. How do we actually go about that decision to do that? And we kind of have these three main structures. We have a steering committee, which really kind of steers the direction and kind of makes a lot of these decisions. At the moment, that's myself, Stuart Mumford, and Shane Maloney. These are termed positions, so we will again they'll be opening again in a year and a bit, and then there's a whole voting system. We also have project custodians, which help kind of drive, I guess, some of the decisions of the steering committee. Again, these are kind of voted in, and people that have been developing with SunPy for a long time to kind of help maintain it. And then we have an advisory board, which is led by Will Barnes, which again, of course, also then advises the steering committee in direction. And people on this advisory board aren't even necessarily developing with SunPy, but they're kind of people within the solar physics community, which will help guide the direction of how this goes. And the reason we kind of changed our governance structure a little bit was if we start to get funding, we need to have a way to distribute that funding, decide on directions we're going in. And this is kind of the structure of the community at the moment. But it's not just we're sitting here, the steering committee and project custodians, it's a community-driven effort, right? We are trying to do the best of what the community needs, what the solar physics community needs. So we're trying to find ways to make this community larger and more sustainable. So we really want to grow it. We need more contributors. So that if you are using SunPy and you hate it, that's a huge, we really need people like that to tell us what is wrong. So this is kind of a kind of view of the community, right? We have the SunPy maintainers and people that are on that governance structure, the solar physics community, which is you. And then we also have a lot of people from outside, people who contribute. So say we have some software developers that kind of fly by who aren't solar physicists, but can help us from the software perspective. And this is also another aspect of our community. And the question is, how do we all talk to each other on GitHub? We also have our element chat, which I'll talk a bit about in a moment. But I guess the key takeaway is we really need your input. The idea of showing this slide is that we're all those people, we're all the solar physicists. I'm not funded to do SunPy. This is a community-driven effort. And this is just the structure in which we make these decisions. So how do you contribute to SunPy? If you are interested in this, you like SunPy, you hate SunPy, but you wanted it to get better, how do you actually get involved? And a lot of people think you need to be a really good coder and software developer to come and contribute code and to look at the GitHub and understand what's going on. And that's absolutely not the case. I think we do not need, you do not need to know how to make a pull request or to read GitHub code to contribute to SunPy. If anything, we need more of the latter. We need more of feedback. We need to know from the solar physics community, from the users, specifically people who are using it, what works, what doesn't work, and what would you like to see. So this is a big problem we have, is that when those of us that work on SunPy knows what it can do and kind of are blind to what's not clear. So we need to have user feedback to help guide better documentation or to guide gaps in SunPy that are not there. Also, another way to then contribute, like if you have feedback, how do you actually then give that feedback? One way is through GitHub. So you can raise issues on GitHub. So this is just a screenshot. If you go to GitHub SunPy, there's a button that says new issue. And if you click on that, you can see there's this whole kind of list of things you can add. So it can either be a bug, something's not working as expected. You can request a feature. You're like, hey, I'd love SunPy to be able to work with this data or to do this thing. If something's really slow or anything else, or if you just want to come and chat to us, this is one place. We also have our element chat, which is almost like a Slack, where you can just come by and say hello or show kind of cool things you've been doing with SunPy. That's another way of contributing to SunPy. And then, of course, code, right? If you do want to contribute code or you're interested in contributing code, we'd love to have you. We have this kind of marker called good first issues on a lot of our issues. So this is ones we have listed as, oh, well, this is an issue that needs to be fixed in SunPy. It's not too complicated, so it's a good one for someone to start. So this could be adding a new feature, fixing a bug, adding an example to the example gallery. That's one really nice way to kind of get in. And it doesn't necessarily need to be on SunPy Core. It can be a little bit challenging now in SunPy Core to actually add new code because it is quite stable, but our affiliated packages actually do need a lot of help from a maintenance perspective, but also to add some more things in there. And they can be iterated on a lot quicker from a review process. So if anybody's interested, I'd also suggest to look at our GitHub of our affiliated packages. We also, on our documentation, on our webpage, we have this newcomer's guide, which kind of gives description again of how to contribute, whether it be code or not code. If you're contributing code, you'll see there's kind of a whole sequence of things you might need to do. If you don't even know how to do any of them, that's no problem. Please come and talk to us, and we really would love to help you or to guide you in terms of that process. I myself, when I started to get involved in SunPy during my PhD, I had absolutely no idea about how these tests run, and I was seeing all these errors when I tried to make a pull request. But again, just working with each other and trying to learning as we go, I think that's the best way to get involved. On our community, we have lots of ways you can talk to us. I think the best way, if you're interested, is in go to our chat. This is an Elements chat. This is a screenshot from it where people just ask questions about specific things. This is an example of somebody looking for calibrated LASCO data. We also have a discourse page on open astronomy, which we're also trying to get more and more people to use. So this could be, we see it as kind of like a Stack Overflow place for people to post questions that are kind of then tracked because sometimes they get lost in a chat. We also have a presence on Helionauts if anybody's there. And we also have weekly calls on a Wednesday at 5 GMT. And they're welcome. They don't need to be SunPy developers. You can come on and say hello. So again, we're really trying to grow this community, and please get involved if you're interested, or even if you just need help. If you want to do something for your paper and you don't know how to do it, please just come and ask, and we're always happy to help. So what's next for SunPy? I've kind of given you an overview of where we are, what our history is, our affiliated packages. But in the next, on our roadmap for even just the next year, what are our plans for developing big kind of changes within SunPy? The biggest one we've actually been working on for a while is to modernize map, right? So to date, a SunPy map has to be a two-dimensional map, right? So what about the third dimension, whether that be in time or in wavelength? So we want to actually be able to have underneath the hood. So from a user perspective, you don't know any different, but underneath it will actually be an n-dimensional cube structure. At the moment, it's just an ND data structure, and then we carry around this WCS. But we would actually want to integrate this to be an ND cubed underneath the hood. This is a lot of work we've been trying to do, but why we're trying to do this, and we're hoping this would be in our next large release of SunPy, maybe in 8, and so in version 8, is that it then enables that if you have kind of a sequence of maps, you can slice through different ways. We have a way to do a map sequence now, but it's challenging to take a slice through. So that's one way we want to do. And then also then have support, not just in time, but also in wavelength, as I said. So you can imagine having a sequence of images at one time that have different wavelength dimension, whether it be in frequency space. So say if you have radio observations, you might have images at different frequencies, or it could be, a spectrogram, so you have lots of different energies or wavelengths, and kind of have a unified way to do that. So from an infrastructure point of view, for SunPy underneath, we're trying to make everything in ND cube. While SunPy mostly is not funded, right? It's not long-term funded. We don't have sustainable funding from anywhere. Sometimes we write proposals as a committee, as a governance body of big things. We're trying to get support to kind of pay some people's time for doing this. We were actually successful last year, even given the NASA situation. We have yet to see if we will get this money, but our proposal was accepted, and it should be awarded. And this was a proposal basically to look at enhancing NDCube a little bit more, which will help with the first point, for working with different workflows. So again, abstracting away from a user, what dimension you're working in, and also for time series improvement. So we also don't have a lot of support in time series for certain in situ measurements that we want to improve. and we want to have better light time and time handling across multiple missions. And this is becoming more and more important with Solar Orbiter. So this will actually fund some of our developer time to actually spend 100% of their time working on this and actually contribute to SunPy in that way. And what is the sustainability of SunPy, right? I guess if you forget everything else, just think SunPy is not this organization that has, sits up on is the SunPy company. Absolutely not. We're just scientists trying to develop something. And we've kind of gotten to a point that most scientific workflows depend on SunPy, right? But even just maintaining it, even if we don't develop anything else, maintaining it is a substantial ongoing effort, right? It takes time to make sure that things aren't broken, dependencies aren't broken, and if a server goes down, to make sure there's a backup server for FIDO search and things like this. So sustainability of the SunPy ecosystem, it takes people, it takes time, and for both of these things, what you need is long-term support. So it's a community-driven effort. We're really not funded. We have written some proposals, mainly through NASA calls in the past, where we've gotten kind of a small grant money that we could pay one of our developers their time, their FTE time, to actually work dedicated on this rather than just taking it out for doing their own research. Most of the time it's maintained by researchers like myself or others, where like I have no funding to do this, so you're trying to do this on top of everything else. And it is really a continuous effort. And I just want to, maybe this is a bit cheeky to say, but missions make data, right? They make the data, but for scientists, you really need the software and the community to actually make that science. So in terms of sustained investment, it's great to fund new missions, but you need to make sure that the funding is also there to create software that is going to survive and that works well, looking to the future. So with that, I'll kind of finish, some summaries about SunPy. I didn't really go in to show you any code or to show you any really examples of what we can do, but just to kind of give some backstory about the ecosystem and where it's going. The SunPy project is this whole ecosystem, right? SunPy is not just the core package. It includes the core package, the affiliated packages, and everyone, contributors and users. It's really good for solar physics observations, but it does also extend out for doing lots of different heliophysics research. So depending on what you're doing, historically it has had most support for remote sensing instruments, and that's solely based on the fact that the people that were developing it were remote sensing scientists. So it would be great to have more in situ people getting involved and kind of saying what needs their data it have for including within SunPy. So that's definitely within scope and something we're looking to do in the future. I think SunPy, it's come a huge way since 2011. It's making solar data more accessible, consistent, and importantly reproducible. So even though we're on SunPy 7.1, you can go back and install SunPy version 3, and you can reproduce a paper that produced that code or produced their plots with 7.3. So it's version 3. It's kind of a way to kind of make sure that we can do reproducible science. Kind of bridges missions, instruments, and communities. It's growing and evolving. We're always kind of trying to think of new things we can put in, and it's really built by the community. So we'd love people to get involved, whether you are a master's student, a PhD student, a postdoc, a senior faculty. And again, getting involved doesn't mean contributing code. It can also mean things like telling us what you need, what works, what doesn't work, and thinking maybe of interesting ways we can maybe support this infrastructure in the future. So with that, I'll finish, and hopefully we have some time for discussion. Thanks very much.
Thank you so much, Laura. It was perfect on time, so we can maybe start with the questions. There are some questions in the chat, so maybe we can start with that. Chitradeep, do you want to ask yourself?
Yeah, thanks, Eddie. Thanks, Laura, for this beautiful summary of SunPy, as always. Maybe you have touched upon this already in your presentation in some of the workflow, but I was just wondering from the mission PI's perspective, once the data sets are available, what's the typical workflow to integrate those data sets to SunPy, more specifically with FIDO?
Yeah. That's a great question. I think the best workflow in a way is it could even be before your instrument flies, but even when you have it now, is to maybe raise an issue on GitHub, right? It could be you can raise an issue and say, hey, I have this new data. What's the next port of call? So that could be then we can maybe decide, okay, well, do you need more help, or is it just we point you in the direction of writing it in a certain way? We also could invite you to come to our weekly calls and have that discussion. So I think the best thing to do is just reach out, whether it be on GitHub, whether it be on the chat, or send some of us an email and we can kind of point in that direction. I think that's the best way. Just open communication is the best way to start. Again, if you kind of go into the newcomers guide, we also have some descriptions of adding in how to create your own FIDO client. We also have a SunPy package template. So say, for example, you're a PI and you say, great, I want to make my own package for the data that works well with SunPy. You can actually take the SunPy template and start to build within that. So I think, to make a long story short, just come and reach out and we can kind of then point in the right direction of the approach to go.
Great, thank you.
Then there is some question from Swarup. Do you want to ask yourself? Okay, I can ask on his behalf. He's asking about an open data workshop so that we could have first-hand experience of SunPy or any other way amateurs could understand it better. So if we can have such kind of workshops anytime soon.
Yeah, that's a great point. And this is something we've talked about within the SunPy group, is like, would there be an appetite for that, right? Because we were thinking of maybe doing an online, 3-day summer school type workshop where it's not about the science, right? It's specifically about working with SunPy. And then we can do things of, how to work with the data, start from scratch of getting the data, doing interesting things with that data. And then also a way to, I guess, develop the new generation of people that will help sustain SunPy. So, I mean, if that's something that you think would be interesting, maybe this is something we could think about as a SunPy community and maybe do something similar to what this amazing workshop you guys have done and do it online. If that's something people are interested in, please let us know. And this is definitely something we could consider. We have several tutorials online and old ones we've given at workshops on our GitHub if you want to have a look. But again, they might be out of date, but it's definitely something we could think about in the future.
Okay, thank you. Any more questions? You can raise your hand and ask yourself.
Yeah, Ketki, my hand is raised.
Okay, sorry. Go ahead.
Okay. Yeah, hi, Laura. Great, very inspiring talk. And deep appreciation for the SunPy team. I have two questions. First, from the aspect of getting involved with SunPy. Let's say if I have developed a Python package and I want it to be inside SunPy, there's also option of Helio Python PyHC. So what would you suggest? Which platform or community, are they working together or are they separate things?
Yeah. So HelioPy is no longer exists. Everything that was in HelioPy, we've kind of, in one way, I think we've kind of ate it, right? So everything that was in HelioPy now exists within SunPy, and HelioPy no longer. Within Python and Heliophysics community, so that's like a community that try to bring together people who are developing packages. So SunPy is one of the parts of Python and Heliophysics. That's a really good point. If you have code and you don't know where it should go, I think, again, coming to talk to us, because it could be that it's an affiliated package of SunPy. And what are the kind of next steps you might need to integrate it into being an affiliated package? The Python Heliophysics community is also a great place because there are lots of other packages there. So going there and even just discussing what you have. I think some of the challenges we have with people that come by and say, hey, I have all this great code, let's put it in SunPy. Sometimes it can be a huge amount of work to change it in such a way that it works within SunPy core, and that pushes people away. And we really want that not to happen. So a suggestion is, if you are thinking, well, maybe you already have a package, but if somebody else is thinking of developing new code, I would say start to talk early rather than later, because it's hard after the fact to go back and integrate it more with SunPy. But if you start at the get-go of like, okay, well, what does it need to work well with the ecosystem? Maybe a data container already exists that I can extend on. That kind of makes that workflow a little bit better. But again, I think the best thing is just to come and say, hey, I have this cool thing, point me in the right direction. Which seems to be my answer for everything. But it's kind of, again, it's this community-driven thing of trying to kind of find what's already out there or kind of collect efforts of each other's.
Yeah, okay, got it. And my second question was that, is there any discussion of extending it to PyTorch, like including the differentiable pipeline, since a lot of usage on like AI, even in solar heliosphere is happening. So is there any plan to make it differentiable?
to make it so so can you repeat that within PyTorch, did you say?
To make it differentiable, like introduce PyTorch, give an option that this is already a differentiable pipeline, just take it and use it in your machine learning thing, something like that.
Yeah, we've kind of done some efforts of that. I know people have worked on it. We don't have anything really specific within SunPy that would need to necessarily change for you to run it within PyTorch. We have some support now for um, loading maps into Dask arrays, right, which is kind of important for doing this large data. But if there's a specific thing you need from the SunPy backend that would help you with that workflow, please raise an issue. We don't have any integration at the moment, but of course it's something we're thinking about. We're living in this big data era. How can we make SunPy work in a way with pipelines that people are interested in? So the short answer is no, not yet, but there are kind of some ways you can kind of change things to work in that way. But again, let us like flag it somewhere that you're interested in this, and maybe some effort can be put into to updating that.
Yes, definitely. Thank you.
Yeah. Then there is one more question in the chat from Kakul. Do you want to ask yourself?
Yes, I would like to ask. Hi, Laura. It was great listening to your talk. I just have a quick question that if you could deprecate one legacy part of the SunPy code tomorrow to make the library faster or cleaner, which part would it be and what is stopping you?
Yeah, that's a really excellent question, and maybe we'll be here all night. What is the biggest thing? I think the biggest thing that's kind of, if we could go back, delete something and start again, I think some aspects of map underneath the hood, we would start again and we would, this integration I talked about NDQ being underneath, that is something that is slowing us down because map already exists. A lot of people use it and we don't want something to break all of a sudden. So a lot of the challenges with trying to make sure this legacy happens with map and put this in is that we're having to kind of mash around NDQ to make sure the functions work the same. And that's really slowing it down. So it would be great to be able to completely deprecate and start again in that one aspect. I think there's nothing that's really there that we're like, oh my God, we wish that wasn't there anymore. A lot of that was actually cleaned in the version 1 release. But I think it's more just now, trying to change dramatic things just takes a lot longer because we have to ensure this, we have a very long deprecation period and the legacy code still works. And, this is a problem of any major package. I'm sure like NumPy have this issue and Pandas. But I think map, the way it's kind of was written and evolved over the years, I think taking a step back, if we could start again from scratch, it would almost be a little bit easier. But that's not something, we're not going to go and break maps, so nobody needs to worry. But that's a great question.
Thank
And
you,
I'm sure
Laura.
that also would change if you asked somebody else within SunPy. But from my perspective, that's what I would say.
Yeah, thank you so much.
Yeah, I also want to ask one question. It's like if you have like data restriction, kind of like it's not available when the data is available, and if they are changing the versions, how that affects the pipeline in the SunPy?
So do you mean like if data is behind like a password wall or something like that? Is that what you mean?
Yeah.
Yeah. This is a big challenge, right? Because first of all, we can't really write in plugins that work with that. And I guess if we say we're pulling from, for just an example, say we're pulling from the Solar Orbiter archive and we have a way that we know and we test that, we get that data down, it reads into map and great. And we have one search. But all of a sudden, if a data provider starts to provide you, even with the same query, a different data product and it breaks everything, that's really big. Like, how can we can't do anything about that.
Exactly.
So what we're trying to do is we are saying, like a lot of time people say, well, SunPy doesn't work to get AIA data, it's broken again. And that's not actually SunPy's fault. That's actually the JSOC having issues. But that's how, so I guess it's a challenge. And I think the way we have to go around it is just communicate about understanding what it's doing underneath the hood. It's just going to get that data. If that data is provided differently, that's not really on us. And then also build up relationships with the data providers. So, for example, we have a very good relationship with the Solar Orbiter archive. We know them well, and they talk to each other, talk to us. They say if it's going to be down, we'll know and we can flag it. So again, it's just this community effort. We need to make sure that everyone's invested. If you are a data provider, you're invested in knowing where people are getting your data. Is it through SunPy? Then they need to talk to us in that way. But for sure, that is a challenge. But I think it is getting a lot better in that way. And in solar physics, it's great that we are usually quite an open data community, right? Most data is open source and openly available once it's down. Yeah.
Okay, thank you. Any more questions? If not, then we can thank Laura. Thank you so much for such a nice talk.
Great,
and
thank you so
all
much.
the question and answer session. Thank you so much. And now we come to the end, and we would like to have, this is our last day. So we want to have a closing ceremony of Indus. And so we have a small presentation. I hope everyone can wait and be patient for this. I'll share my screen. Can you see the screen?
Yes.
Okay, thank you. Okay. So yes, as I said, this is the last day. So I just want to go through highlights of all these 3 days. Just okay. Okay. So this was our schedule at glance. We were really packed for all these 3 days. We divided our schedule in the morning session, Indian morning, and Indian evening session. We had 4 phases in total in every day, and total 6 sessions, scientific sessions. And we got a lot of contributions from solar atmosphere session and heliospheric structure and transients. So for the day 1, we almost had 200 plus participants that is showed on Zoom, which is a great achievement because we also had participants 200 plus. And we had 3 scientific sessions. In total, 2 of them were contributed oral presentation sessions and 1 was for flash talks. So we had 11 contributed oral presentation that were presented and 3 contributed flash talks were presented. Then afterwards, we continued with the panel discussion. And for all these contributed talks, we had 3 chairs as well. So we thank all the chairs who generously agreed to be the chair of the session and very well conducted all the sessions. Then we also thank our moderator who conducted all the panel discussions and all the panelists. And finally, we continued with the invited talk by Matthew West on the first day, who gave a nice talk on vision mission. On the second day, we again continued with the same format. Again, the same 200 plus participants we had, 3 scientific sessions with the same 2 contributed presentation and 1 flash talk. We had 9 contributed oral presentation and 4 flash talks on the second day, and 3 session chairs again. And the topic for the panel discussions was frontier and future direction in space weather research. And I think everyone liked this panel discussion very much. And then we continued with the invited talk by Enrico on AI for space weather. And the last day today. So this was the number for the morning session. So I don't have the complete number yet, but I hope it's the same as last 2 days. And I also want to point out that for every session, we had a number of participants attending between 40 to 60 constantly. So I would like to say that there was like, of course, incoming flow and outgoing flow of participants. But in total, we had like 200 plus participants throughout the day. And we had the today's day was really packed. We had 3 scientific sessions and all of 3 were contributed sessions. So we had 16 contributed oral presentation, and these contributed oral presentations conducted by 3 session chairs, and we just had our panel discussion and was moderated by Dibendu Nandi, who is present here. And then we recently had the invited talk by Laura on Sanpai. So for this was the first meeting that we have organized through Indus, ISHA, and to organize that, this was our the first experience. So we needed a solid backbone for that, and so this is our advisory committee, who was a solid support system for us. Ankush Bhaskar from ISRO VSSC, Anshu Kumari from PRL USO, Dipedu Nandi from SESI ISAR Kolkata, and Nitin Yadav IIT Delhi. We really want to thank all these people and thank you for all your support throughout. And finally, but not the least, of course, our team, organizing committee. We started all this discussion about ISHA around October or something, and from then we are constantly working on that. We had a lot of discussions, lot of meetings, and you can see that we are all from different time zones. So it was very difficult to have a meeting at one point and then agree on all the points. We had, of course, a lot of disagreements as well as a perfect team. But finally, we tried to get everything together, and you can see that ISHA went very well. So thank you to all the team members. And lastly, stay tuned for all the recordings because we have recorded all the sessions and you will get that on YouTube. So we will be compiling that soon and you will receive an email about that. So you can scan this QR code for the YouTube channel. You can follow us, subscribe us, and stay tuned with us. And lastly, we also want your feedback. Please let us know what we can do better and what you want from us because we really want to continue ISHA every year, possibly. So please let us know your thoughts. And that's how I want to conclude. But before that, I also want to hear some things from our advisory committee. So Dibendu Nandi is here. So I would like to give the floor to him to say something about ISHA.
Thank you, Ketaki, for first of all inviting me to be the convener for today's panel, but more importantly for involving me in this initiative. Not just ISHA, but Indus, the network, I think is something very unique and exemplary. I have not seen such a community building exercise anywhere else in the world run by students and postdocs, those at very early stages in their career, and being run so efficiently and so usefully. Even my students have often said that they have learned things and gained from day-to-day interactions with other community members who are part of the Indus community. I think this is a selfless exercise in the sense that each of you could in principle be competing with each other, which I think anyway we are all doing, but we could also be helping each other gain better ground so that when I help you climb up, you help me climb up as well, right? This is often lost on many people. I think this nice, I think, ecosystem you're building, I hope that this will really have an impact 5 years, 10 years down the line. And I believe that you have the support of the senior members, the faculty members of the community in a big way, because we do recognize the value that you bring in to the ecosystem, which makes us complete and sort of does things which we cannot spare time to do. But which is something that is very important for keeping the community alive, sustain it, and in fact, make it thrive. So on behalf, I don't see anybody else who's senior, but on behalf of all of us, I express my sincere gratitude to all of you for doing this. Very, very, from the bottom of my heart, really. So I hope to be associated with you and wish you all good luck.
Thank you so much for the kind words. And I can see Anshu is also here. Do you want to say something, Anshu?
Yeah, hi. First, I would like to thank Divyandu for such encouraging words for Team Indus. We are very happy, at least I am very happy the way it is going on for the past 2.5 years. And I agree that we had all the support from the community since Indus was started. So apart from that, I am very happy how this symposium took place. I could only join a few sessions due to other commitments, but I'm very happy how the team as well as other people who worked behind it have executed this. So very good. All the best for next Indus ISHA symposium.
Thank you, Anshu. Ankush is also here. Do you want to say something, Ankush?
Oh yeah, I just joined. Yeah. Actually, it was fantastic. The organization done by you all young guys is really nice. Making the website, getting a nice panelist. That is also, I found like panels were very balanced. So, and this was a need of time for India to have such vibrant community of youngsters. And I'm sure with time it will keep growing and contribute to Indian space science and even global science. So wish you all the best. That's it I have to say.
Thank you so much. Some words from organizing committee. Pratik, do you want to say
Okay.
something?
Yeah, maybe I can lead, then others can join. Yeah, it was very overwhelming feeling. We have been working on this for several months now. And to be honest, these 3 days were seeing that fruit being flourished after so much of effort. And thanks to the team, as Ankush mentioned, website, Sirsho is handling the website. You might be seeing this background, those nice, cool, every graphics looks awesome. That is done by Chitdeep and Keti. Soumya is there. You see newsletter every time. Trust me, it takes a huge amount of work to send it every time. Sometimes there is some delay, some link might not work, but kind of we are working on top of our research. So yeah, it's a great feeling to be part of this team. Great.
Now we also want to give the floor to participants if someone wants to say something.
Yeah,
No words.
anyone open mic? Yeah. Any feedback, any remark? Which session was the best session? What you like the most? What you would like to see in the next edition? Something we missed? Any comment remark? Please, that will be really, really helpful.
Hi, I'm Marisha. Actually, I am from a part of India which is very remote side of our India. Here, the people doing research in solar physics is very less. I one or two. This is the first time I am doing my PhD. This is my third year. This is the very first time I am attending a seminar or a symposium solely dedicated for solar physics. That is enough for me. Actually, that's only give me the best feeling ever because all the seminars I am attending mainly dedicated. The topic itself says nano physics are mainly related on solar physics. See, mainly related on other material sciences. But this is the first time I am finding a community which is working fully on this solar or heliophysics. That gives me a hope of doing a better work in future. Thank you.
Yes, thank you. Thank you very much. This was one of the goal of ISHA actually, that to open platform for everyone. And thankfully, and we are glad that we have achieved that. Anyone else want to go? Okay, if you feel shy, please don't forget to at least fill the feedback form. There you don't have to speak, but we will be really looking forward to the feedback form. So, and here I want to conclude ISHA meeting and hope to see you in next ISHA very soon. Thank you so much.
Thank you. Thank you, Jyoti. And just to add one thing at the end, a little advertisement. We are looking for new or fresh, motivated volunteers. Please go through the website or join the Indus WhatsApp group. I will post a form there as well. We need fresh PhDs or anybody who is interested in kind of being part of Indus and contribute. Thank you.
Yeah. And also, I think next some in-person meeting we should do sometime. That will be also nice.
Yes.
We would also like that. Yes.
And I also would like to add one point here. We have so many members. Show Indus some love on social media as well. They do a lot of good stuff. Please have a look, if be it Twitter, LinkedIn, whatever, wherever you are, because they are doing good stuff. They do post very good thing and new opportunity. Go follow them on social media as well, because that's the best way to connect.
right. Thank you
Thank you
very
so
much.
much.
I have to leave now. Thank you all again. Take care and happiness.
Bye.
Thank
Bye.
you.
Thank you.
Bye.
Bye.
Everyone. Bye-bye.
Thank you, sir.
Thank you, sir.
Yes, sir. Thank you.
Great, guys. Chalo. Pratik and team, very nice job. Keep it
Thank
up.
you.
Okay, thank you, Ankush.
Bye.
Bye-bye.
Bye-bye.
Scientific is a great session. Thank you, sir.
Thank you.